Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're opening the door to something so familiar we barely notice it, and yet so strange it keeps the sharpest minds awake at night. We're going to settle into the question of what space and time actually are. Not just the practical side of them that keeps our calendars in order or helps us find the bus stop, but the deeper reality behind the words we use so casually. Space, the stage where everything seems to happen, and time, the rhythm that carries us from one moment to the next. Together they hold our entire existence, but when you look closely, they start to wobble and slip through your fingers. Before we set off, let me ask you something. Where are you listening from right now? Are you curled up in bed with the light dimmed, or maybe stretched out on a couch in the late afternoon, trying to let the day soften its edges? Perhaps you're in a different time zone than I am, drifting toward night or moving through morning. What time is it for you, in your little corner of the world? It's a simple question, and yet it sits right at the heart of what we're about to explore. Because what we mean by now and what we mean by here are not quite as straightforward as they feel. If this gentle journey gives you calm, if you find it soothing to drift along through big ideas without hurry, I'd be ever so grateful if you tapped the like button or subscribed. It helps this quiet corner reach other people who might need a soft place to think and rest too. So take a deep breath, let your body ease into whatever surface you're lying on, and let's begin. Because the question of space and time is not just about equations or textbooks. It's about the invisible backdrop of your entire life, the thing that cradles every breath you take, every glance at a clock, and every night you fall asleep under the sky. When you look around your room right now, what do you actually see? Maybe a lamp, maybe a wall, maybe the ceiling above you. But surrounding all of those things is something else, something you don't see directly. You call it space. You know it's there because objects sit in it, because distances stretch between them. But what is it really? Is it a kind of container that holds the universe? Or is it nothing at all, an emptiness that gains meaning only when things exist inside it? For most of human history, people didn't have a clear answer. They just lived in it. They built houses, planted fields, drew maps, and pointed at stars, all without really knowing what this invisible arena was. And then there's time. You've already felt it passing as you listen. You know it's moving because these words arrive one after another, never all at once. The world doesn't come to you as a frozen photograph. It comes as a sequence. That's what gives life its shape, its story. And yet, when you ask what time actually is, the answer becomes slippery. Is it a flowing river that carries us along? Or is it something built into our own perception? A trick of memory and attention? We spend our days saying things like, I don't have enough time, or time flies, or that took forever. But those phrases mix objective clocks with very subjective feelings. The closer you look, the blurrier it gets. That's why tonight we're going to let ourselves walk slowly through the history, the science, and the mystery of these two things that seem so obvious yet are so puzzling. You don't need to worry about solving anything. You don't need equations or diagrams. Just a willingness to notice how strange it is that anything exists in the first place, and how curious it is that we experience it unfolding moment by moment. Let's imagine just for a second that you could peel everything away. Every wall, every floorboard, every piece of furniture, every atom of your body, every star, planet and galaxy. Strip the universe down until nothing material is left. Would there still be something? Would there still be space stretching on in silence? Or would you be left with nothing at all, not even emptiness, just the absence of everything, including the stage itself? That question has haunted philosophers for thousands of years. Some thought space was like a container, a box that exists even if it's empty. Others argued that space is only the relationship between objects, so if you remove all objects, space disappears with them. And if you try the same thought experiment with time, the puzzle deepens. Take away every event, every motion, every tick of every clock, every thought in every mind. Would time still be flowing, or does it only exist when something changes? Is it like a backdrop ticking away whether or not anything happens? Or is it simply the way we describe change, nothing more than a measure of how one moment differs from the next? These questions aren't just idle musings. They shaped entire civilizations, and they laid the foundations of modern science. The earliest people looked up at the night sky and saw the stars shifting positions. They noticed the sun rising and setting, the moon growing full and then vanishing to a sliver, the seasons bringing warmth, cold, harvest, and hunger. These repeating patterns gave them their first tools for thinking about space and time. The sky became a giant clock and a giant map marking where and when they were in the world. But those early observations also revealed the strangeness. Why do stars move the way they do? Why does the sun return at just the right place each year to bring back spring? Is the world at the centre of everything, with space wrapped around it like a dome? Or are we moving too, part of some larger dance? Without telescopes, they could only guess, but they already sensed that space was not just emptiness, and time was not just passing. They were ordered, regular, almost like something was keeping track. As we drift forward tonight, we'll be visiting many of these ideas in more detail. We'll see how ancient civilizations used shadows and flowing water to measure passing hours, how Newton pictured space and time as rigid, absolute frameworks, how Einstein bent them into a flexible fabric, and how modern physics sometimes questions whether they exist at all in the way we think they do. Along the way, we'll step into black holes, stretch with the expanding cosmos, shrink down to the quantum scale, and even pause inside the rhythms of your own body. But for now, it's enough to simply notice that these two things we take for granted, space and time, are not simple at all. They are the deepest background of your life, and yet they slip through definition like water through your fingers. They are everywhere, and yet nowhere you can point to. They hold everything, and yet they may not even be things at all. That's what makes them such a gentle puzzle to settle into tonight. The vastness of space is something we all know about in a casual way, but very few of us ever stop to consider what it truly means. You glance at the sky on a clear night and see tiny points of light, and your mind accepts that they are stars, far away. But how far away? And what does it even mean for something to be far in a place where there are no roads, no walls, no boundaries? When you say a star is millions of light years away, you're pointing to something much stranger than just distance. You're pointing to the idea that there exists a kind of stage large enough to hold unimaginable spans, yet completely invisible, completely intangible, and yet somehow real. When we think about space, it's tempting to picture it as a kind of box. A box without edges, but a box nonetheless. A container that holds planets, galaxies, dust, and us. This is a very natural way to imagine it, because all our experience is with containers. A room holds furniture, a jar holds water, a basket holds fruit. So why not think of the universe itself as just a bigger version of that? But if you pause long enough, you start to realize that space is not simply a container. It is not something that sits there waiting to be filled. It is woven into the very fabric of reality. Without it, the idea of where becomes meaningless. Philosophers in ancient Greece argued fiercely over whether space was a real thing or simply a way of talking about the arrangement of objects. To someone like Democritus, who believed in atoms, space was just empty void, the nothingness in which atoms moved. To Aristotle, this made no sense. He thought nature abhorred a vacuum, that true emptiness could not exist. What we call space, he said, was not a thing in itself, but only the set of relationships between objects. Move an object and you change space. Remove objects, and there is nothing left to call space at all. For centuries, this debate shaped how people understood the world. Was space a real background, or just a word? the problem became sharper as humans began to measure things more carefully. Think of an ancient builder setting up a temple. They laid out the foundation stones by sight and by rope. They measured distances by pacing them out or using rods. They aligned walls with the sun's path. In doing so, they were not just building, they were defining space. They were taking something invisible and turning it into order, into lines and shapes that could be shared and repeated. This was practical, but beneath it was the bigger question. Is the order in space something we impose, or is it there on its own, waiting to be discovered? When the telescope was invented, space became even stranger. Galileo pointed his telescope at the heavens and found not just stars but moons circling Jupiter. He found that the Milky Way was not a pale streak of light, but millions upon millions of stars crowded together. He showed that space stretched much further than anyone had ever imagined. The container box image began to strain. How big could this container be? Was it infinite? If it had an edge, what was outside the edge? If it had no edge, how could that be possible? These questions did not have simple answers then, and they still don't now. We often take comfort in maps. A map gives us boundaries, a place to put names. But space resists mapping. You can chart stars on paper, you can mark distances, but no matter how large the map grows, there is always more beyond it. The act of drawing a map of space is like chasing the horizon. No matter how far you go, the edge recedes. This is because space is not something that ends somewhere. It stretches as far as we can tell, and it may well stretch without limit. Our instruments can only see so far, limited by the speed of light and the age of the universe, but there is no evidence that beyond that horizon lies a wall or a boundary. Space is also not just emptiness. Even in the parts of the universe that appear empty, there are particles popping in and out of existence, fields vibrating, energy shifting. Quantum physics tells us that what we call empty space is actually buzzing with activity, more like a restless sea than a quiet void. This challenges our old intuition that space is nothingness. It is not nothing. It is a dynamic part of reality, shaping and being shaped by matter and energy. When you move through it, you're not moving through emptiness. You're moving through a medium that has structure, laws, and effects. Think about gravity. For a long time, gravity was thought of as a force acting at a distance. Newton's great insight was to describe it mathematically, to show that the same force that pulls an apple down also keeps the moon in orbit. But what he described was still action at a distance, objects attracting one another across empty space. This was unsettling even to Newton. He did not pretend to know how such action was possible. He just described what he could measure. It wasn't until Einstein came along that a new picture emerged. Einstein described space not as emptiness, but as fabric. A flexible fabric that can bend, stretch, and ripple. In this view, space and time together make up a single entity called spacetime, and mass and energy tell this spacetime how to curve. The curve, in turn, tells matter how to move. What we call gravity is really objects following the curves in this fabric. Planets orbit stars not because they are being pulled by an invisible hand, but because the fabric of space-time around the star is curved and the planet is simply rolling along that curve. Suddenly, space was not passive. It was active, shaping motion. This idea has been confirmed again and again. The bending of light around massive objects, the slow drift of Mercury's orbit, the detection of gravitational waves rippling through space itself, all show that space is not empty nothingness. It is something with properties, something that can bend, something that can stretch, something that can vibrate. But even this picture leaves questions. If space is a fabric, what is it woven from? What is the loom on which it is stretched? Einstein's equations describe how it behaves, but they do not tell us what it is. At the smallest scales, our theories break down. Quantum physics and relativity clash. Some scientists think that space might not be fundamental at all. It might be an emergent property, like temperature. No single molecule has a temperature, but when you gather trillions, temperature emerges. Perhaps space emerges from something deeper, some network of relationships we do not yet understand. This leads to a very strange possibility. What if space itself is not continuous? What if, at the tiniest scales, it is granular, made up of tiny bits? Just as matter is made of atoms, perhaps space is made of discrete units, woven together like pixels on a screen. At large scales, the pixels blur into smoothness, but underneath there might be a deeper structure. Some theories in physics explore this idea, though no one has yet confirmed it. For everyday life, space feels stable. You know the distance between your chair and the table. You know how far you have to walk to reach the door. These distances don't change in ordinary circumstances. Space feels like the most reliable thing there is. But on the cosmic scale, it is dynamic. The universe itself is expanding, which means that space between galaxies is stretching. Galaxies are not flying apart into pre-existing emptiness. The space itself is growing, carrying them with it. This is a difficult idea to grasp because it defies our box container intuition. The universe is not expanding into something, space itself is unfolding. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see evidence of this expansion. That glow is stretched light, lengthened by the growth of space. Every photon that reaches us has been travelling not through static emptiness, but through a stretching medium. The universe we see is like a snapshot frozen on the surface of a balloon that is still being inflated. Space itself grows, carrying everything along. For you, listening here and now, the room around you may feel utterly still, utterly ordinary, but it is part of this vast stage. Every object you see is suspended in the same fabric that stretches across billions of light years. The quiet air around you is linked to the structure of galaxies. The space you occupy is not separate from the cosmos. It is the same thing. The question of what space really is remains open. Is it a real thing, or is it just the name we give to relationships between objects? Is it continuous or discrete? Is it fundamental or emergent? Our best theories give us powerful descriptions, but they have not yet given us final answers. Perhaps there may never be a final answer. Perhaps space is simply the word we use for the arena of existence, the silent vastness that allows anything at all to be somewhere. You know the feeling of glancing at a clock and being surprised by what it says. Perhaps you thought an hour had passed when in fact it was only 10 minutes. Or perhaps you believed just a few minutes had gone by when an entire afternoon slipped away. This little mismatch between what the clock shows and what your mind feels is a reminder that time, for us, is not just a number on a dial. It is an experience, an invisible thread woven through your senses, your attention, and your memory. The world's clocks may tick steadily, but the way you feel their rhythm is far less steady. Imagine sitting in a waiting room with nothing to do. The walls are plain, the chairs are uncomfortable, the air is quiet except for the ticking of a clock on the wall. Each second seems to drag, each tick lands with more weight than the one before. Now compare that to an evening spent in conversation with a friend. Hours can vanish in what feels like minutes. You don't notice the clock at all because you are absorbed. The difference between those two experiences tells us something profound. Time is not just measured by external devices, it is also constructed by your brain. Psychologists often talk about subjective time. This is the inner sense of when things begin, how long they last and when they end. Unlike the objective time on a clock, subjective time is flexible. It stretches, shrinks, and sometimes disappears altogether. What shapes this inner sense are your levels of attention, emotion, and memory. If you are focused on every detail of a situation, time feels slower. If your attention is elsewhere, time slips away. If you're afraid or anxious, time drags. If you're joyful and absorbed, it flies. One of the most powerful influences is novelty. When you encounter something new, your brain devotes more resources to processing it. It lays down more memories. Later, when you recall the experience, it seems as if it lasted longer than it really did. That is one reason childhood summers often feel endless. Each day is filled with new sights, new experiences, new moments being logged in detail. As adults, routines take over. Fewer new memories are recorded, so looking back, whole years can feel compressed. Life seems to accelerate, not because time itself is faster, but because your brain is capturing fewer landmarks along the way. Another factor is emotion. In fearful or dangerous situations, people often report time slowing down. Someone who has been in a car accident or a sudden fall may describe everything happening in slow motion. Scientists studying this effect have found that it is not that the world actually slows down, but that the brain under stress takes in more information per second. Later, when recalling the event, the dense memory makes it feel as if time stretched. Joy and excitement have the opposite effect. They lighten attention, reduce the sense of detail, and make time feel like it is running quickly. Then there is boredom. When the mind has nothing engaging to occupy it, your brain's internal timekeeper seems to overcount. Every second is noticed, every pause is heavy. The brain becomes its own metronome, beating insistently, making moments feel longer. Neuroscientists sometimes describe this as the brain's pacemaker, firing more actively, creating more mental pulses to count. This is why idle waiting feels longer than active doing, even if the actual time is identical. Cultural background also shapes how people sense time. In English, time is often spoken of as a resource. We talk about spending time, saving time, wasting time, or running out of it. This creates an image of time as something flowing past us like money through our hands. Other languages frame it differently. Some describe time as a landscape, something you move through rather than something that flows past you. In some cultures, the future is imagined as being behind you, unseen and unknown, while the past is imagined in front of you, visible and already travelled. These different metaphors affect how people feel time. They shape whether the future feels like something rushing toward you or something you're walking backward into. Beneath all of this sits biology. Your body carries its own clocks, not just the circadian rhythm that guides sleep and wakefulness, but shorter timers as well. The brain has mechanisms that track seconds and minutes. These involve networks in the basal ganglia and cerebellum, using steady neural pulses as a kind of internal stopwatch. When you estimate how long something lasts, your brain is counting these pulses. But this system is easily disrupted. Multitasking, distraction, or strong emotion can scramble the count, making your estimates unreliable. That is why you might be surprised by how long a meeting felt or how quickly a walk passed. There is also a curious phenomenon called the return trip effect. When you travel to a destination, the journey often feels longer than the return, even if the distance and time are the same. One explanation is that on the way there, your brain is processing new information, logging the route. On the way back, the route is familiar, requiring less attention, so the experience feels faster. This is a small example of how perception of time is not about clocks at all, but about how your brain handles information. Even sleep shows how fragile your sense of time is. Think of the snooze button. Those 9 minutes between alarms often feel shorter than any other 9 minutes in the day. It's not that the clock changes, but that your brain in a half-sleep state is not tracking time normally. It slips, collapses, and feels shorter than it is. The sense of time also changes across the lifespan. For children, waiting 5 minutes can feel like forever. Their brains are still learning to judge duration, and their sense of proportion is different. For a child, a year is a huge fraction of their lived experience. For an adult, it is a much smaller fraction. This scaling means that as you age, each year feels shorter in comparison to the whole of your life. That shrinking proportion is another reason why decades can seem to pass in the blink of an eye once you're older. Some people also experience unusual perceptions of time due to altered states of consciousness. Deep meditation, certain neurological conditions, or even the influence of substances can make time seem to stop, loop, or dissolve entirely. In meditation, for example, focusing on the present moment reduces attention to duration, making time fade away. In some conditions, like temporal lobe epilepsy, people report vivid distortions of time, such as minutes feeling like hours or moments repeating. These experiences highlight how much of time is bound to the brain's processing rather than to external reality. There is also the fascinating case of flow, a state where you are so absorbed in an activity that you lose track of time altogether. This can happen while playing music, creating art, solving problems, or even while playing games. Hours can vanish without awareness. Psychologist Mihaly Csikszentmihalyi described flow as a state of complete engagement, where your skills are balanced with the challenge at hand and self-consciousness disappears. In this state, time does not just speed up or slow down, it almost ceases to exist for you. The threads of time in your mind are also connected to memory. You can only remember the past, never the future. Memory lays down traces in the brain, and those traces are what give you a sense of sequence. Without memory, there would be no sense of before or after. You would exist in a perpetual now, with no thread connecting one moment to another. This shows that time, as you experience it, is not only external, it is woven through the very function of your brain. All of this suggests that time is both universal and personal. The universe may run on regular rhythms, but the way you feel them is deeply human. Clocks may measure seconds precisely, but your mind measures them differently depending on attention, novelty, emotion, culture, and biology. This creates the strange situation where two people sitting side by side may experience the same hour very differently. As you listen now, you might even notice the effect happening. If your mind is relaxed, if you're absorbed in the story, time may seem to pass more quickly than it otherwise would. If you're distracted, time may seem to drag. Either way, the actual clock ticks the same. This disconnect between outer time and inner time is what makes our experience of life so fascinating and sometimes so confusing. It also raises a deeper question. If time is experienced so differently by each person, what does that say about time itself? Is it truly a thing outside of us flowing steadily? Or is it partly a construction of consciousness? Physics tells us that time can warp under gravity, stretch at high speeds, and maybe even disappear in certain equations. Psychology tells us that time bends with attention, memory, and mood. Somewhere between those perspectives lies the reality we live in. For now, it is enough to recognize that your sense of time is not absolute. It is elastic, shifting with what you do and how you feel. It is made of invisible threads spun from your own brain. The steady tick of a clock and the gentle stretch of an evening in conversation are both real, but they are not the same. One is measured from outside, the other is lived from within. And it is this lived sense of time that colours your days, giving some moments weight, others lightness, and some the feeling of vanishing altogether. Long before telescopes, long before equations, long before the word universe even existed, people looked up at the sky and wondered what it meant. The night sky was the first book, the first map, the first calendar. It stretched over every village, every field, every sea, silently displaying patterns that returned again and again. Those patterns became the earliest way to understand space and time, long before those words were spoken in the way we use them now. Imagine someone thousands of years ago standing in an open field at night. There are no city lights, no electric glow, just the stars above, sharp and countless. The Milky Way is not a faint haze as we often see it now, but a blazing river of light across the darkness. The moon rises and sets, the stars rotate through the night, constellations climb and fall. These were the first reliable signs of order in the world. The ground could change with weather, rivers could flood, forests could burn, but the sky kept its rhythm. Early humans used this rhythm to survive. The rising of certain stars marked when the seasons would change, when to plant crops, when animals would migrate, when the rains would come. In Egypt, the rising of the star Sirius just before dawn signalled the flooding of the Nile, a vital moment for farming. In Mesopotamia, careful observers mapped the motions of planets, predicting when they would appear and vanish. These were not idle stargazers. They were building the first science of time, even if they would not have called it that. The sun was the most obvious guide. Its daily path across the sky gave the first measure of day and night. Shadows lengthened and shortened, showing the passage of hours before the word hour existed. By marking where shadows fell, people created sundials, some of the earliest tools for dividing a day. These were not perfect, since the length of the day itself changes with the seasons, but they gave a structure to daylight that could be repeated. With sundials came the first hint that time could be divided into pieces, that the day itself could be measured and planned. The moon offered another rhythm, slower and softer. Its phases repeated in cycles from crescent to full and back again. These cycles gave rise to months, a natural way to count longer stretches. The word month itself in many languages comes directly from the word for moon. Farmers, sailors and priests all watched the moon carefully, using its changes to predict tides, to plan rituals, to schedule festivals. In many ancient calendars, the months were tied directly to the moon, and the new moon was often the marker of a new cycle of time. Then there were the stars, which offered the longest rhythms of all. Over the course of a year, constellations shifted positions in the sky. Some became visible only in certain seasons. This gave people a way to mark the year, long before mechanical calendars. Watching the skies closely, people could know when winter was coming, when spring was near, when it was time to harvest. The stars became a memory device, a way to store time in the sky itself. All of these rhythms, the sun, the moon, the stars, were not only practical, but also deeply meaningful. People wove them into stories. Constellations became hunters, animals, heroes, and gods. The cycles of the moon became symbols of birth, growth, and death. The rising of the sun became a metaphor for renewal, its setting a metaphor for rest. These stories gave space and time human meaning. They turned abstract patterns into something that could be remembered, shared, and lived by. Different civilizations developed different systems to capture this order. In Mesopotamia, the Babylonians divided the circle of the sky into 360 degrees, a choice that still shapes how we measure angles and hours today. They track the motions of planets, noting their loops and retrograde paths. These records were not just observations, they were the beginnings of astronomy. They showed that space could be mapped and that time could be predicted. In Mesoamerica, the Maya built intricate calendars that tracked both the solar year and cycles of ritual time. One of their calendars, the Long Count, could measure spans covering thousands of years. The Maya saw time not only as a cycle, but as a great unfolding pattern, with each era marked by cosmic events. For them, time was sacred as well as practical. Space and time were not separate ideas, but part of the same sacred order of the cosmos. In China, observers recorded eclipses, comets, and planetary motions for centuries. They built instruments to measure the positions of the stars with remarkable accuracy. Their calendars combined solar and lunar cycles, creating a careful balance that guided agriculture and festivals. These records were not only about survival, but also about legitimacy. A ruler who could predict celestial events was seen as having the mandate of heaven. In this way, the sky became a political tool as well as a scientific one. In ancient Greece, philosophers began to argue more abstractly about what space and time really were. Pythagoras and his followers believed that numbers and harmony underlay the universe. They saw the motions of the planets as a kind of music, a harmony of the spheres. Plato spoke of time as the moving image of eternity, a way for the eternal order of the cosmos to be seen in the changing world. Aristotle, on the other hand, described time as the measure of change, something that could not exist without motion. For him, time was not an independent entity, but a way to count change in the world. Space, too, was debated. Was it a real thing, a container, or just the arrangement of objects? These debates set the stage for later science, showing how humans were already grappling with the abstract nature of the very background they lived in. Stone monuments also show how ancient people marked space and time. At Stonehenge in England, massive stones are arranged in a way that aligns with the sunrise on the solstice. Similar alignments can be found in monuments across the world. These were not just places of ritual, but also observatories, ways to track the sky with the earth itself as the instrument. Building such monuments required careful observation, planning, and a sense of the sky as something predictable and orderly. As centuries passed, the ability to measure time became more refined. Water clocks or clepsydras appeared in Egypt, Greece, and China. These devices let water flow steadily from one vessel to another, measuring time in a way that did not depend on the sun. They could be used at night, offering a new independence from daylight. Some were elaborate, with gears and figures that moved as the water flowed, turning time into spectacle as well as measure. All of these efforts, the watching of stars, the tracking of shadows, the building of clocks, reveal something about the human relationship with space and time. These were not just practical matters of farming or ritual. They were also about control and understanding. By marking the rhythms of the sky, people felt connected to the larger order of the cosmos. They could predict, plan, and give meaning to their lives. But beneath these practical uses, the deeper questions remained. Was space infinite, or did it end somewhere? If it ended, what was beyond? Was time a cycle, repeating endlessly, or was it a line moving forward? Different cultures gave different answers. Some saw time as circular, tied to the cycles of nature. Others began to imagine it as linear, with a beginning and an unfolding future. These differences shaped how people thought about history, destiny, and even the meaning of life. For all their differences, what unites these ancient views is the recognition that space and time are not obvious. They are not things you can hold in your hand or see directly. They are frameworks, patterns, backdrops. The ancients may not have had modern physics, but they already sensed that to understand the world, one must understand the stage on which it plays out. Even now, when we look back at those ancient skies, we can feel a connection. The same stars they saw still shine, the same sun still rises, the same moon still changes phase. The tools and theories may have changed, but the wonder is the same. And that wonder is what drove humans to first mark time with shadows and stars, to map space with stones and stories, and to begin the long journey of trying to understand the invisible frameworks that hold our lives. If you close your eyes and imagine the very first clocks humans ever made, chances are you picture a sundial, a simple stick casting a shadow, with marks on the ground to show how the shadow shifts as the sun moves across the sky. It feels ancient, elemental, almost obvious. Long before gears, springs, and atomic oscillations, the sun and its shadows gave us our first tools for measuring change. They turned the passage of daylight into something visible and shared, something you could point to and agree upon. But sundials were not the very beginning. Even before formal devices were built, people noticed shadows as natural markers. A tree, a rock, a standing stone all threw shadows that lengthened and shortened as the day went on. By watching these patterns, early observers could tell when it was morning, midday, or evening. Over time, they began to mark these observations more deliberately. A pole in the ground, placed upright, would serve as a gnomon, the simplest tool for tracking the sun's journey. The gnomon's shadow became a kind of silent hand on a clock face written in the dirt. What made sundials so powerful was their reliability. The sun returned every day, rising and setting with dependable rhythm. By marking where shadows fell at different times of year, people could not only divide the day but also predict the seasons. In Egypt around 1500 BCE, small portable sundials were carved from stone. These devices had notches or lines to indicate divisions of time. They could be carried and set up in the sunlight, giving a traveller or a worker a way to know the hour. Imagine holding one of these in your hand, tilting it in the sun, and seeing time appear in the length of a shadow. Sundials, however, had their limitations. The length of daylight changes with the seasons, so the hours measured by a sundial were not always equal. In summer, daylight hours stretched long, making each hour longer. In winter, daylight hours were short, making each hour shorter. These so-called temporal hours were uneven, tied directly to the changing seasons. This worked well enough for agricultural societies, where tasks followed the rhythms of nature, but it would feel strange to us now, used as we are to fixed hours that tick by at the same pace year-round. As societies grew more complex, the need for more precise and consistent measures of time increased. Sundials evolved. The Greeks refined them, building elaborate versions like the hemicycle, a half bowl cut into stone with a gnomon casting shadows onto marked lines. The Romans spread sundials across their empire, setting them in public squares so citizens could see the time of day. In fact, one complaint recorded in Roman writings was that sundials forced people to notice time too much, dividing their days more strictly than before. What had once been a natural rhythm became a schedule to obey. Even then, timekeeping was beginning to shape social life, but sundials had another obvious flaw. They only worked when the sun was shining. Cloudy days, early mornings, and night time made them useless. This limitation led to the development of other devices like water clocks, but before those innovations spread, people learned to combine methods. In some cultures, sundials set the standard during the day, and at night the moon, stars, or water clocks took over. The division of the day into measured parts was becoming a shared human project, no longer left only to natural rhythms but increasingly formalized by tools. The very act of dividing time changed how people thought. When you cut a day into hours, you create units that can be planned, scheduled, and coordinated. A farmer can meet a neighbour when the shadow is at this mark. A priest can hold rituals at fixed times. Workers can be called together at agreed hours. Sundials were more than simple devices. They were instruments of organisation. They turned time into something external, something you could look at and measure together. Not all sundials looked alike. Some were horizontal, laid flat on the ground. Others were vertical, mounted on walls. Some were aligned carefully to the latitude of the place so that the gnomon's angle matched the tilt of the earth. This allowed for greater accuracy, showing the growing understanding of geometry and astronomy. In China, large sundials were built in observatories, serving both as scientific instruments and as symbols of authority. To command time was to command order, and rulers often associated themselves with these great instruments. Portable sundials also became popular. Some were small enough to be carried in a pocket or a bag. They often required careful alignment with the direction of north, showing how people learned to combine knowledge of the Earth's orientation with the sun's movement. These devices remind us that measuring time was not just about abstract science. It was a practical skill, woven into travel, trade, and daily work. Beyond their technical uses, sundials also had symbolic meaning. The shadow of the gnomon was often seen as a metaphor for life itself, growing and shrinking as the day moved on, disappearing at sunset. In many cultures, the movement of the sun and its shadow became a reminder of mortality, of the fleeting nature of human existence. Inscriptions on sundials sometimes carried sayings like, "I count only the happy hours," or "time flies." Even in ancient times, people reflected on the emotional weight of passing hours, not just their utility. The spread of sundials also connected different cultures. Designs travelled along trade routes, adapted and refined by each society. The Greeks learned from the Babylonians and Egyptians. The Romans borrowed from the Greeks. Knowledge flowed across borders, carried by merchants, soldiers, and scholars. Each culture added its own refinements, but the basic principle remained the same. The shadow of the sun can measure change. Of course, sundials could never fully solve the problem of cloudy days and nights. That is why water clocks, candle clocks, and later mechanical clocks emerged. But sundials never fully disappeared either. Even today you can find them in gardens, parks, and public squares. They no longer serve as primary timekeepers, but they remain as reminders of our oldest way of dividing the day. A sundial in a garden invites you to pause, to notice the slow movement of the shadow, to connect with a rhythm older than machines. What sundials reveal most clearly is that the human desire to measure time is not new. From the very beginning, people wanted to mark change, to make the invisible visible. Watching shadows was a way of taming the day, of giving structure to the flow of experience. Once you begin measuring, you never quite stop. Each new method, sundials, water clocks, mechanical clocks, atomic clocks, becomes a refinement, but the impulse remains the same, to grasp the slippery thing we call time and hold it still if only for a moment. And behind that impulse lies a deeper connection to space itself. A sundial does not only measure time, it measures the relationship between the Earth and the Sun. Every shadow cast is a direct record of the planet's rotation, of its place in the cosmos. To read a sundial is to read not just the hour, but your position in the universe. It ties you to the sky in a direct and tangible way, reminding you that your daily routine is linked to the turning of the Earth beneath the Sun. So the next time you see a sundial, whether in a park or a picture, remember what it represents. It is not just a quaint decoration. It is a relic of humanity's earliest attempts to capture change, to organize life by the movements of the heavens. Its shadow carries the weight of thousands of years of curiosity, practicality, and reflection. It is the ancestor of every clock you have ever checked, every calendar you have ever followed, and it whispers the same message today that it did in the beginning. Time is passing, shadows are moving, and the day is unfolding whether you count it or not. By the time the 17th century arrived, human beings had already spent thousands of years watching shadows, tracking stars, and building increasingly clever tools to measure the passing of hours. But there was still no single picture of what space and time truly were. The sky had been mapped, calendars refined, clocks improved, yet the question remained unsettled. Were space and time things in themselves, flowing silently in the background, or were they just the names for change and motion? It was into this debate that Isaac Newton stepped, bringing with him a vision so clear, so compelling, that it shaped science and everyday thinking for centuries to come. Newton lived in an age when the natural world was beginning to be described with new precision. The Renaissance had stirred a fresh appetite for mathematics and observation. Galileo had pointed his telescope to the sky and shown that Jupiter had moons, that Venus had phases, and that the heavens were not the perfect unchanging spheres Aristotle had described. Johannes Kepler had uncovered mathematical laws governing planetary motion, showing that planets traced ellipses around the sun. But the deeper why was still unanswered. What force moved the planets? Why did they not fly off into the void? What held the cosmos together? Newton's great insight was to connect the falling apple with the orbiting moon. The same force that pulls an apple to the ground, he argued, also keeps the moon circling the Earth and the Earth circling the sun. That force was gravity, and it was universal. He gave it mathematical form, showing that it decreases with the square of the distance. Suddenly one law explained both the motions of the heavens and the motions on Earth. There was no longer a sharp divide between celestial and terrestrial. The universe was unified under one principle. To make this picture work, Newton also had to describe space and time themselves. He did not treat them as vague backgrounds, but as absolute entities. For him, space was infinite, unchanging, a vast stage on which all events unfolded. Time was absolute too, flowing steadily and uniformly, independent of anything happening within it. He described it as absolute, true, and mathematical time of itself and from its own nature, flowing equably without relation to anything external. In other words, time ticked on at the same pace everywhere, whether anything happened or not. Space was the arena, and time was the universal clock. This was a powerful vision. It meant that motion could be measured precisely, forces calculated, predictions made with confidence. If you knew the positions and velocities of objects, you could, in principle, calculate their future positions. The cosmos became a grand machine, running according to strict laws, each part moving in harmony with the others. This image of a clockwork universe gave scientists and philosophers alike a sense of order and reliability. The world was no longer a place of mysteries governed by hidden influences. It was a lawful system, transparent to reason and mathematics. Newton's framework also gave rise to a new kind of confidence. If the universe was a machine, then by discovering its rules, humans could predict and control nature. Engineering, navigation, astronomy, and physics all flourished under this assumption. Ships sailed with more certainty, guided by better maps and clocks. Architects designed buildings with new structural understanding. The Industrial Revolution, which followed in the next century, carried forward this sense of mechanical order. Even society itself began to be imagined in clockwork terms, regulated, efficient, running on time. But the success of Newton's vision was not just practical. It shaped imagination and culture as well. Writers and thinkers spoke of the universe as a vast watch, wound up by God and then left to run according to its laws. This metaphor of a divine watchmaker became common. It satisfied both the religious desire for a creator and the scientific desire for natural law. The idea that the world was an orderly mechanism resonated deeply, offering stability in a time when old ideas were being challenged. Yet, even in Newton's day, not everyone agreed. His rival, Gottfried Wilhelm Leibniz, argued that space and time were not absolute things but relations. For Leibniz, time was the order of events, and space was the order of coexistences. Without objects, there would be no space, and without change, no time. Newton countered that absolute space and time were necessary to explain true motion. To him, relative motion alone was not enough. If a bucket of water was spun, the water's surface curved. Newton argued this showed rotation relative to absolute space, not just relative to other objects. This bucket argument became a famous point in the debate. Despite such disagreements, Newton's view carried the day. The clarity of his laws, the accuracy of his predictions, and the immense practical success they brought gave his picture dominance. For more than 2 centuries, Newton's universe was science's foundation. It trained minds to think of the world in terms of forces, trajectories, and absolute frameworks. The clockwork image was not only convincing, it worked. But what exactly made this vision so enduring? Partly it was its simplicity. Space and time as absolutes are easy to picture. They give a clean backdrop. They remove ambiguity. In Newton's world, you can say exactly where something is and exactly when it happens. You can set up coordinates in infinite space and tick a clock that flows identically everywhere. That clarity made mathematics and physics manageable. Another reason was its alignment with everyday experience. In ordinary life, time does feel absolute. A minute is a minute no matter where you are. Drop an object here or there and it falls the same way. Space also feels absolute. You measure distances, draw maps, build structures, and it all fits into a consistent framework. Newton's model matched intuition, which made it all the more persuasive. Still, there were cracks. Certain problems nagged at the edges. Gravity, in Newton's theory, acted instantly at a distance. If the sun suddenly vanished, Earth would feel it immediately. This action at a distance troubled even Newton himself. He admitted he could not explain how such influence could cross empty space with no medium. He left it as something not feigned with hypotheses, a gap in the otherwise mechanical picture. For centuries, people accepted the success of his laws without resolving this discomfort. What Newton gave the world above all was predictability. If you launched a cannonball, you could calculate its path. If you watched the planets, you could chart their orbits. If you wanted to design machinery, you could rely on forces and motions behaving consistently. This predictability made science cumulative, building layer upon layer of knowledge. Each generation could rely on the framework and extend it further. Culturally, Newton's universe encouraged a view of life as orderly and rule-bound. The metaphor of the clock spread into thinking about politics, economics, and philosophy. Some began to imagine that if all particles' positions and velocities were known, the entire future could, in principle, be calculated. This idea, called determinism, suggested that the universe was like a film already written, with no surprises. While not everyone accepted such a rigid view, it flowed naturally from Newton's laws. And yet time always has its surprises. By the 19th century, experiments with electricity and magnetism began to reveal oddities. Light did not behave exactly as Newtonian physics expected. The speed of light appeared stubbornly constant, no matter the motion of the observer. Small discrepancies in planetary orbits hinted that something was missing. These anomalies built up until, in the early 20th century, Einstein proposed his theory of relativity, which would overturn Newton's absolutes. But in Newton's era, the sense of mastery was profound. For the first time, humanity had a unified mathematical description of the cosmos. The apple falling from a tree and the moon orbiting the Earth were governed by the same law. That unity was intoxicating. It was as though the universe had finally revealed its blueprint, and with it came a sense that everything was knowable if only we applied reason and calculation. It's worth remembering that Newton himself was a complex figure. While he gave us this rational, mechanical vision, he also devoted much of his life to alchemy, biblical chronology, and hidden meanings in scripture. He was not the purely rational scientist often portrayed in textbooks. His work on gravity and motion was extraordinary, but his personal quest included mysteries and secrets. Perhaps that too is part of why his vision resonated. It balanced the mechanical and the mystical, offering laws that worked while still leaving space for wonder. When you think about Newton's universe today, you can see its traces everywhere. Every clock ticking on your wall, every map showing distances, every calculation of speed or acceleration, all lean on Newtonian principles. Even though relativity has replaced absolute space and time in modern physics, Newton's framework still works beautifully for most everyday situations. Engineers, architects and builders still use his equations. Airplanes fly, bridges stand, rockets launch, all guided by Newtonian mechanics. His vision may have been reshaped, but it was never discarded. So when you picture the world as a great machine, steady and reliable, you are echoing Newton's idea. When you think of time as a steady flow and space as a vast stage, you are living in his universe, even if science has since revealed deeper complexities. His clockwork cosmos is still ticking in our minds, even as new theories bend and twist its gears. By the time the 19th century was ending, Newton's picture of the cosmos still seemed unshakable. His laws of motion and his vision of absolute space and time had guided centuries of discovery. They had steered ships across oceans, built bridges and machines, mapped the paths of planets, and given people confidence that the universe was understandable and orderly. But science has a way of uncovering cracks in even the most solid-seeming walls. The closer experiments looked, the more they revealed small puzzles that Newton's system could not quite explain. The motion of Mercury around the Sun was a little off from predictions. The behaviour of light refused to bend to expectations. Something deeper seemed to be hiding beneath the old framework. Into this world of growing questions stepped Albert Einstein, a young man working as a clerk in a patent office in Switzerland. He was not a professor or a researcher with a laboratory. He was reading papers, filing inventions, and thinking relentlessly, with a stubborn curiosity that would not let go. In 1905, at the age of 26, he published a series of papers that would begin to reshape physics. One of those papers introduced the theory of special relativity, and with it, the first unravelling of Newton's absolutes. Special relativity grew from a simple question: what happens if you chase a beam of light? According to Newtonian thinking, speeds should just add up. If you move toward a light beam, you should meet it faster. If you move away, it should seem slower. But experiments had shown that light always moved at the same speed, no matter how you chased it. This was not a quirk, it was a law of nature. Einstein took that fact seriously, and instead of trying to force light into Newton's framework, he rebuilt the framework itself. The result was radical. He showed that space and time are not absolute. They are relative, depending on motion. If you move quickly compared to someone else, your measurements of time and distance will not agree with theirs. Time for you will tick more slowly. Distances for you will shrink. What had once seemed like fixed backgrounds, space and time themselves were flexible, shifting with speed, and yet the speed of light remained constant for all. This was the strange harmony of relativity. That was only the beginning. A decade later, in 1915, Einstein introduced his general theory of relativity, a deeper evolution. He asked not just about motion, but about gravity itself. Newton had described gravity as a force acting at a distance. Einstein saw it differently. He pictured space and time not as empty backgrounds, but as a single fabric, woven together into what he called spacetime. Mass and energy did not simply sit in spacetime. They bent it, they curved it, and the curves of spacetime told objects how to move. Planets orbited stars not because of an invisible pull, but because they were following the curves in this flexible fabric. This picture was astonishing. It turned the universe from a machine running on invisible strings into a dynamic stage that shaped itself. Imagine placing a heavy ball on a stretched rubber sheet. The sheet dips, curving downward. If you roll smaller balls across the sheet, they will spiral toward the heavy ball, not because it pulls them directly, but because the surface itself is curved. This analogy is not perfect, but gives a glimpse of the idea. Space and time themselves are not rigid containers. They bend, stretch, ripple, and twist. Einstein's vision soon found confirmation. In 1919, astronomers observed a solar eclipse and measured how starlight bent as it passed near the sun. The stars appeared slightly shifted from their usual positions, just as Einstein had predicted. Space itself was bending the path of light. This made headlines around the world. Overnight, Einstein became a symbol of genius, and relativity became not just a theory but a cultural event. The rigid absolutes of Newton had given way to something far stranger and more flexible. The consequences of this shift were profound. It meant that time does not tick the same everywhere. Near a massive object, time slows down. Far from gravity, it speeds up. This is not just a curiosity. Satellites orbiting Earth experience time differently than we do on the surface. Without correcting for this effect, GPS systems would quickly drift and fail. Relativity is not only an abstract theory, it shapes your daily life every time you check a map on your phone. It also meant that the universe itself could expand, contract, or warp. For centuries, people had thought of the cosmos as mostly static, an endless stage where events played out. Einstein's equations allowed for a dynamic universe. Space itself could grow or shrink. At first, Einstein resisted this idea. He even added a term, the cosmological constant, to keep the universe static. Later, when Edwin Hubble observed galaxies rushing away from us, showing that the universe was indeed expanding, Einstein reportedly called the constant his biggest blunder. The cosmos was not fixed at all. It was alive with motion, stretching on the largest scales. Relativity also predicted black holes, regions where space-time curves so intensely that not even light can escape. At first, these were seen as mathematical oddities, too strange to be real. Over time, evidence built. Stars were seen orbiting invisible companions. X-rays revealed matter falling into unseen wells. Finally, in recent years, telescopes captured the shadow of a black hole itself, glowing at the edge of the abyss. Einstein's wobbly fabric was not only a metaphor, it was the real texture of the universe, capable of producing some of its most extreme phenomena. One of the most delicate predictions of general relativity was gravitational waves, ripples in spacetime itself, moving outward when massive objects accelerate. For a century, they remained undetected. Then, in 2015, scientists announced they had observed them directly, waves from two black holes colliding more than 1 billion light-years away. Instruments had recorded the faint stretching and squeezing of space-time itself. It was a triumphant confirmation, as if the universe had whispered directly in Einstein's language. The beauty of Einstein's picture is that it combines the vast and the intimate. It tells you that when you drop an object, it is following the curves of space-time around Earth. It tells you that when you look at a clock on a satellite, its ticking is slowed by both motion and gravity. It tells you that the universe you live in is not rigid but fluid, shaped by energy and mass everywhere. The floor beneath you, the stars above you, the galaxies beyond all share this flexible fabric. And yet, even Einstein's wobbly fabric has limits. At the smallest scales, where quantum physics dominates, relativity begins to break down. The fabric picture clashes with the graininess suggested by quantum theory. Physicists today are still searching for a way to reconcile these views, to see whether space-time itself is emergent from something deeper. But the framework Einstein gave us remains one of the greatest achievements in human thought. It reshaped how we see ourselves in the cosmos. For you, listening now, it can be strange to imagine that time itself is not steady, that your experience of seconds and minutes depends on where you are, how fast you move, and how massive the objects around you are. But this is the reality Einstein revealed. Time is not the universal river Newton imagined. It is a local stream curving with the land it flows through. Space is not an infinite container, but a fabric that stretches, bends, and ripples with energy. Together they form a cosmos far stranger and richer than anyone had imagined, before Einstein's quiet, stubborn insights rewove the stage itself. When Einstein first wrote down his equations of general relativity, he uncovered a truth that even he hesitated to accept. Those equations suggested that the universe could not remain static. Space-time itself could stretch or contract, carrying galaxies with it. At the time, most people believed the cosmos was eternal and unchanging, a vast stage that had always been there and would always remain. The idea that the universe itself could grow larger over time felt unsettling, even absurd. Einstein himself introduced an extra term, the cosmological constant, to keep things steady. He wanted the universe to sit still, but the mathematics whispered otherwise, and soon the sky would reveal the evidence. The story of expansion begins with careful observation. In the early 20th century, astronomers were improving telescopes, building instruments large enough to see beyond the stars of our own Milky Way. One of them, Edwin Hubble, working with the 100-inch Hooker telescope in California, began to measure the light from distant nebulae. Many thought these fuzzy patches were just clouds of gas within our galaxy. Hubble's work showed something different. By studying variable stars known as Cepheids, he measured distances. These nebulae were far beyond the Milky Way. They were galaxies in their own right, each an island universe filled with billions of stars. The cosmos was larger than anyone had imagined, but there was more. Hubble also examined the light from these galaxies, breaking it into spectra, the rainbow of wavelengths. What he found was a shift. The lines were moved toward the red end of the spectrum, a sign that the galaxies were moving away from us. Not just one or two, but almost all of them, and the farther away a galaxy was, the faster it seemed to recede. This pattern became known as Hubble's law. Space itself was stretching, carrying galaxies apart. The universe was expanding. This was a radical discovery. It meant the universe had not always been the way it is now. If it is expanding today, then in the past it must have been smaller, more compact, more dense. Wind the clock backward far enough, and you arrive at a beginning, a time when everything was gathered into a single state. This idea would later be called the Big Bang, though at first it was resisted. Some scientists preferred to imagine a steady-state universe, with new matter continually appearing to keep density constant. But over time, evidence piled up in favour of expansion from a hot, dense origin. One of the most compelling pieces of evidence came in 1965, when two engineers, Arno Penzias and Robert Wilson, accidentally detected faint microwave noise while working with a radio antenna. At first they thought it was interference, even blaming pigeons nesting in the equipment, but the signal persisted. It turned out to be the cosmic microwave background, the afterglow of the early universe, stretched into microwaves by billions of years of expansion. It was a snapshot of the cosmos when it was just 380,000 years old, filling the sky in every direction. This glow confirmed that the universe had indeed begun in a hot, dense state and had been expanding ever since. Expansion is not like objects flying apart into empty space. It is space itself growing. Galaxies are not moving through a pre-existing void. Instead, the distance between them increases because the fabric of space-time is stretching. A common analogy is to imagine dots on the surface of a balloon. As the balloon inflates, the dots move apart. None of them is at the centre. All of them see the others moving away. That is what expansion means, except that our universe expands in all directions, not just across a surface. This expansion affects everything on cosmic scales. Light travelling across billions of years is stretched along with space, shifting toward redder wavelengths. This redshift is not due to motion through space, but to the stretching of space itself. When we look at distant galaxies, we are seeing them as they were billions of years ago, and their light carries the imprint of an expanding cosmos. The farther we look, the younger the universe we see. Astronomy becomes a kind of time travel, each observation a glimpse into earlier and earlier chapters of cosmic history. For everyday life, expansion does not change the room you're in or the city you live in. Gravity and other forces hold small scales together. The Earth does not swell, atoms do not drift apart, and your body does not stretch. Expansion matters only over vast distances where gravity cannot keep things bound. Between galaxies separated by millions of light years, the stretching of space-time dominates, pulling them farther apart. Einstein's equations not only allowed expansion, but predicted it could change over time. For decades, scientists assumed gravity would gradually slow the expansion, perhaps even reverse it, leading to a collapse. But in the late 20th century, measurements of distant supernova revealed something astonishing. The expansion was not slowing, it was accelerating. Galaxies were receding faster and faster, as though some mysterious energy were pushing them apart. This force became known as dark energy, a name more of mystery than explanation. It is now thought to make up about 70% of the universe, yet what it truly is remains unknown. The discovery of acceleration transformed cosmology. It meant the universe was not only stretching but doing so ever more rapidly. If it continues, distant galaxies will eventually slip beyond our horizon. The night sky will grow emptier over unimaginable timescales, as expansion carries everything farther away. Our view of the cosmos is temporary, a fleeting window when galaxies are visible. Future observers, billions of years from now, may see only a dark, empty sky, unaware of the universe's true size. This stretching of the cosmos also ties deeply into relativity. Time and space are not separate entities, but woven together. As space expands, so does the distance between moments in time. Cosmologists often speak of the fabric of space-time itself stretching, not just the positions of galaxies. This is why expansion is not motion through space, but the growth of space itself. It is a direct consequence of Einstein's equations, carried forward by the energy and matter filling the cosmos. What makes this picture even more extraordinary is that the universe has no centre. Every galaxy sees the others receding, just as every point on the balloon surface sees all others moving away. To us, it looks as if we are at the centre of expansion, but to any other galaxy, it looks the same. This universality reflects the principle that the cosmos has no privileged place. Wherever you are, the universe expands around you. The stretching of the cosmos also connects to the idea of cosmic horizons. Because light travels at a finite speed and the universe is only a certain age, we can only see so far. Beyond that horizon lies more universe, but forever beyond our reach. As expansion accelerates, that horizon itself shrinks in terms of what we can eventually observe. We live inside a bubble of visibility surrounded by vast regions that we will never know. Expansion is not just growth but also separation, placing limits on what can ever be seen or measured. And yet this grand stretching is also what allowed stars, planets and life to exist. In the early universe, matter was nearly uniform. Expansion cooled it, allowing gas to clump under gravity, forming galaxies and stars. Those stars forged the heavy elements in their cores, scattering them when they exploded. Every atom of carbon, oxygen, iron in your body was shaped in that process. Without expansion, the universe would have remained a hot plasma, too dense and chaotic for structure. The stretching of space created the room for complexity. For you, sitting in your own place and time, it may feel impossible to connect with such scales. But when you look at the night sky, you are seeing directly into this story. Every star is a reminder that the universe is not static but dynamic. The faint glow between stars, the patterns of galaxies in photographs, the shift of light toward red, all carry the imprint of expansion. It is written across the sky, available to anyone who pauses long enough to look. Einstein's wobbly fabric gave us the language to describe this growth. Hubble's observations gave us the evidence. Together they revealed a universe not fixed but alive with motion, a cosmos stretching outward in all directions, and as we continue to measure, we find new mysteries. Dark energy, dark matter, the fate of expansion, all remain open questions. The stretching cosmos is not just an answer, but an invitation. A reminder that space and time are still full of secrets waiting quietly to be uncovered. When you look around the room you're in, your eyes go first to objects: a chair, a table, a wall, a lamp. You notice what is there. What often escapes attention is the space between those things, the empty stretches that appear to contain nothing at all. In ordinary life, we treat that nothingness as unimportant, just background. Yet when you pause and think about it, the so-called empty parts are just as puzzling as the solid ones. What is emptiness really? Is there such a thing as true nothing? Or is the empty space around you hiding layers of activity invisible to your senses? For centuries, thinkers wrestled with the idea of the void. In ancient Greece, Democritus argued that atoms moved in empty space, a void necessary for motion. Aristotle disagreed, insisting that nature abhorred a vacuum. To him, the idea of true nothingness made no sense. Space, he believed, was always filled with something, even if only subtle air or ether. This debate echoed through the ages. Medieval scholars sided mostly with Aristotle, while natural philosophers of the Renaissance began to reconsider. Experiments with pumps and glass tubes showed that air could be removed, creating regions of lower pressure. As technology advanced, scientists learned to make vacuums more complete, pumping out almost all matter. Still, the question remained, was this emptiness truly nothing? When Newton described space, he imagined it as a vast absolute container. Even if you stripped away all matter and energy, he thought, space would remain, stretching endlessly. To him, empty space was a real thing, an infinite stage. It had existence independent of the objects inside it. For others, like Leibniz, this was absurd. If you remove all objects, what is left to define space? How could a stage exist with no actors, no scenery, no play? The debate between absolute and relational space became one of the great philosophical questions of the 17th century. Centuries later, Einstein shifted the picture again. He replaced Newton's rigid container with a flexible fabric, spacetime. Space was not a passive backdrop but an active player, bending under mass and energy. This meant that even what we call empty space was not nothing. It could curve, stretch, and ripple. In this view, emptiness had geometry. It had shape. Remove all matter and energy, and space-time itself would still remain, capable of bending and vibrating. The void was no longer nothing. It was a structure with properties. But quantum physics complicated things further. According to quantum theory, the vacuum is not silent. Even in the absence of particles, fields remain. They fluctuate, bubbling with brief appearances of particle-antiparticle pairs that pop into existence and annihilate almost instantly. This restless activity is called quantum vacuum fluctuations. To the naked eye, it looks like nothing. To sensitive experiments, it is a sea of energy. In fact, one of the most striking demonstrations of this is the Casimir effect. Place two metal plates very close together in a vacuum, and they feel a tiny force pushing them together. This force arises from differences in the quantum fluctuations inside and outside the gap. Even empty space exerts a pressure. This realization, that the vacuum is alive with activity, changed how physicists think about nothingness. What we call empty space is filled with invisible fields, electromagnetic fields, gravitational fields, Higgs fields. They do not vanish when particles are removed. They are part of the fabric of reality. The Higgs field, for example, pervades all space, giving mass to particles that interact with it. Without it, atoms would not exist and matter as we know it would dissolve. So the void is not a barren desert. It is more like an invisible ocean, calm at the surface but churning underneath. Even the concept of energy is tied to the vacuum. Quantum theory suggests that the lowest possible energy state of a field, the vacuum state, still contains energy. This vacuum energy might even be connected to dark energy, the mysterious force accelerating cosmic expansion. If so, then the fate of the entire universe is tied to the properties of what looks like nothing. The accelerating cosmos we see today could be the signature of vacuum energy on the larger scales. On smaller scales, physicists explore whether space itself is continuous or granular. Perhaps what we think of as smooth emptiness is made of tiny units, like pixels on a screen. If that were true, then emptiness would not be continuous at all, but built from discrete pieces at the Planck scale, unimaginably small. So far, experiments have not confirmed this, but the question remains open. Could nothing itself have a hidden texture, finer than anything we can yet observe? For ordinary life, emptiness seems obvious. The room you're in feels filled with air, but if you pump the air out, you would expect to be left with nothing. Yet even then, the walls around you radiate electromagnetic fields. Particles flit in and out, gravity threads through. The so-called empty space is always alive. The universe does not tolerate perfect nothing. Everywhere you look, something hums below the surface. This makes emptiness strangely central to physics. It is not simply absence, but a kind of canvas filled with potential. Particles arise from it. Forces ripple through it. Galaxies drift apart because of it. The nothingness we often ignore is in fact a key player in the unfolding of the cosmos. Even in the emptiest reaches between galaxies, where a single atom may be scattered across cubic meters, the vacuum itself shapes what happens. Light moves through it. Gravity bends it. Quantum fields shimmer within it. The phrase empty space is therefore misleading. What we call empty is anything but. It is filled with invisible structure, laws, and energy. It is the most universal thing in existence, present everywhere, shaping everything, yet never directly seen. Your body is surrounded by it. Your thoughts unfold within it, and your planet sails through it. It is both the background and the medium of reality. For centuries, humans thought of nothingness as a void to be feared or dismissed. Now we know it is more subtle and profound. It is not nothing but something hidden in plain sight. The shape of nothing is the shape of space itself, bending, stretching, vibrating with energy we cannot touch, but can measure in delicate ways. The mysteries of the universe often lie not in what is present, but in what seems absent. Empty space is perhaps the clearest example. And as you sit now listening, surrounded by the air in your room, surrounded by the quiet gaps between objects, it is worth remembering that those gaps are not empty. They are filled with the invisible framework of reality, shaping the way light moves to your eyes, the way sound travels to your ears, the way atoms hold together. The nothing around you is not absence at all, but presence of a deeper kind, waiting patiently to be noticed. When you think of gravity, the first image that probably comes to mind is something falling. An apple dropping from a tree, a stone slipping from your hand, a body pulled downward toward the earth. That picture is simple and familiar, the kind of explanation that feels obvious. Objects fall because gravity pulls them, but the deeper you look, the stranger gravity becomes. It does not just hold you to the ground, it bends light, it slows time, it reshapes the very structure of space. What seems like the most ordinary force turns out to be among the most subtle and mysterious, weaving together effects that stretch from the smallest objects to the largest structures in the cosmos. The shift began with Einstein's general relativity. Instead of describing gravity as a force acting at a distance, he pictured it as the bending of space-time itself. A massive object like the Earth or the Sun warps the fabric around it, and smaller objects follow the curves of that warp. This bending has consequences that reach far beyond keeping your feet on the ground. It means that light itself, which has no mass, can be curved when it passes near a massive body. It also means that time itself, which feels to you like the most steady flow imaginable, can be slowed down by gravity. The bending of light was one of the earliest and most dramatic confirmations of Einstein's ideas. In 1919, during a solar eclipse, astronomers looked carefully at the stars near the darkened sun. Normally their positions in the sky are fixed, but with the sun's mass bending space-time, the starlight travelling past it was curved, making the stars appear in slightly shifted positions. The measurements matched Einstein's predictions, not Newton's. This was a turning point. The universe was not only more dynamic than Newton had imagined, but light itself obeyed the curves of space-time. Gravitational lensing, as it is now called, is one of the most striking ways this effect appears. When light from a distant galaxy or quasar passes near a massive cluster of galaxies on its way to us, the cluster's gravity bends and magnifies the light. Sometimes it creates multiple images of the same object, arranged in arcs or rings. Telescopes capture these ghostly patterns, revealing not only the distant galaxies, but also the invisible mass of the cluster doing the bending. In this way, gravity becomes a natural lens, allowing astronomers to see farther than otherwise possible. It also reveals dark matter, the unseen substance that outweighs ordinary matter in the cosmos, because lensing shows more bending than visible matter alone can explain. The bending of time is just as fascinating, though less visible. According to relativity, clocks run more slowly in stronger gravitational fields. This means that time passes a little differently on Earth's surface than it does far above it. For most of human history, this effect was too tiny to notice. But with modern technology, it becomes critical. Satellites in orbit around Earth experience weaker gravity than we do at the surface, so their clocks tick slightly faster. If GPS satellites did not correct for this effect, their timing would drift by microseconds each day. That may sound small, but it would quickly translate into errors of kilometers in positioning. Every time you use your phone to find directions, you're relying on relativity and the way gravity bends time itself. Even more dramatic differences occur near extremely massive objects. Near a black hole, the warping of space-time is so intense that time slows drastically. To an outside observer, an object falling toward the event horizon seems to freeze, never quite crossing. From the perspective of the falling object, however, time proceeds normally, carrying it inward. This difference shows how flexible time really is. It is not an absolute river flowing the same for everyone, but a local experience shaped by gravity. Einstein's equations also imply that gravity affects energy, and even the colour of light. When light climbs out of a gravitational well, it loses energy, stretching to longer, redder wavelengths. This gravitational redshift has been measured in laboratories and in astrophysical observations. It is another sign that gravity reaches into every aspect of reality, not just pulling matter, but bending the very flow of energy and time. These tricks of gravity are not limited to exotic astrophysical situations. They are present all around you, even if too subtle to notice directly. Every second of your life, your body is immersed in the warping of space-time caused by Earth. Your experience of time is shaped by this invisible curve. Compared to someone floating far from any planet or star, your seconds are a little longer, your minutes a little slower. You would not notice the difference, but it is there, measured with precision by atomic clocks placed at different altitudes. Move a clock just a few meters higher, and it ticks slightly faster. Gravity's influence is inescapable, everywhere and constant. The realization that gravity bends light and time also changes how we think about the universe as a whole. Light from distant galaxies has travelled for billions of years to reach us, threading its way through the warps of space-time created by intervening matter. By the time it arrives, it carries not only the story of its source, but also the imprint of every bend along the way. Studying these distortions allows astronomers to map the invisible scaffolding of the universe, the great web of dark matter that shapes the distribution of galaxies. Gravity, through its subtle tricks, becomes a messenger, carrying hidden information across cosmic distances. This interplay of bending light and bending time is also what makes black holes so fascinating. At the event horizon, the escape velocity equals the speed of light. No light can leave, making the black hole invisible. But just outside, gravity magnifies and distorts the light from surrounding matter. Accretion disks of hot gas glow brightly as they swirl inward, twisted by extreme space-time curvature. The images captured by telescopes of black hole shadows are direct consequences of light being bent almost into circles before escaping. These pictures are not simply photographs. They are portraits of warped space-time itself. Even gravitational waves, the ripples in space-time produced by violent events like merging black holes, are part of this same picture. They are the dynamic bending of space-time travelling outward, carrying energy across the cosmos. When detectors on Earth measured them for the first time in 2015, they confirmed not only Einstein's predictions, but also the reality that space-time is not rigid. It flexes, wobbles, and carries information. These waves are perhaps the most delicate example of gravity's subtle tricks, stretching and squeezing space by less than the width of a proton across kilometers of detectors, yet unmistakably real. All of these effects remind us that gravity is not just one of four forces. It is the geometry of space-time itself, shaping how everything moves and experiences existence. What feels like an ordinary downward pull is actually your body following the curve of space-time toward Earth's centre. What feels like an ordinary beam of light is actually tracing the warps of cosmic structure. What feels like the steady tick of a clock is actually a rhythm slowed or hastened by the strength of gravity around it. For most of human history, none of this was suspected. People thought of gravity as a simple attraction, a pull that kept things grounded. Now we know it bends the paths of photons, shapes the flow of time, and ripples outward as waves. It is one of the most familiar aspects of life, and yet one of the most mysterious. Every glance at the stars, every second on your watch, every signal from a satellite is touched by gravity's tricks. And as you rest, listening now, the same invisible bending is at work. Light entering your eyes has been deflected countless times on its journey. Time flowing through your mind is slowed by the pull of Earth beneath you. The everyday world is full of these distortions, too subtle to feel but woven into reality. Gravity is not just the force that drops an apple. It is the sculptor of space and time, quietly reshaping the stage on which everything unfolds. Black holes are among the most extreme expressions of gravity, and they bring together nearly every puzzle about space and time into a single phenomenon. When you hear the term, it may conjure images of dark abysses swallowing everything nearby, mysterious traps lurking in the universe. In a way, that picture is accurate, but the reality is even more subtle and fascinating. Black holes are not just holes. They are regions where space-time itself has been curved to the limit, where the bending is so intense that no path leads back outward once you cross a certain boundary. They are both terrifying and beautiful, the ultimate test of Einstein's theory, and a window into questions that science still cannot fully answer. The idea of such an object began long before Einstein. In the late 18th century, an English natural philosopher named John Michell imagined a star so massive and dense that its gravity would not allow light to escape. He called it a dark star. The idea was speculative and lacked a clear framework, but it was remarkably prescient. The concept disappeared from discussion for more than a century, until relativity brought it back to life. Einstein's equations showed that if enough mass were concentrated in a small enough region, space-time would fold in on itself, creating a surface from which nothing, not even light, could return. This surface is what we call the event horizon. To an outside observer, the horizon marks the edge of knowability. Once an object crosses it, no signal can get back out. From the inside, however, there is no sudden barrier. Crossing the horizon feels no different than passing through air. But from the outside, it looks as though the object slows and freezes, light from it stretched and dimmed until it fades away. In this sense, black holes embody relativity's deepest ideas. Time itself becomes tangled, different depending on where you stand. To you on the outside, the fall into a black hole seems endless. To the object falling, it is swift and inescapable. At the center of a black hole, according to the simplest solutions of Einstein's equations, lies a singularity, a point where density becomes infinite and the curvature of space-time breaks down. Here, the laws of physics as we know them stop working. General relativity predicts it, but cannot describe it. Quantum theory offers no clear answer either. The singularity is where our current understanding ends, a boundary not just in space but in knowledge itself. Some physicists think the singularity might not be real, but a signal that a deeper theory is needed. Perhaps space and time themselves dissolve at that point, replaced by something we do not yet know how to describe. Black holes come in different sizes. Some form when massive stars exhaust their fuel and collapse, their cores crushed by gravity into a small volume. These stellar mass black holes weigh a few times more than our Sun but fit into a region only a few kilometers across. Others are far larger, millions or even billions of times the Sun's mass, lurking at the centers of galaxies. These supermassive black holes are engines that shape galaxies themselves, powering quasars, shooting out jets of energy that stretch for thousands of light years. The origin of such giants is still uncertain. Did they grow slowly over billions of years, or did they form in the earliest moments of the universe seeded by primordial conditions? The answer is still hidden. Despite their reputation as cosmic vacuum cleaners, black holes do not suck in everything indiscriminately. Objects can orbit them just as they orbit stars, so long as they stay outside the event horizon. In fact, black holes often reveal themselves not by swallowing everything, but by the matter around them. Gas spirals inward, heating to incredible temperatures as it forms an accretion disk. This glowing material emits radiation across the spectrum, sometimes outshining the entire galaxy hosting the black hole. By studying these emissions, astronomers can infer the presence and properties of black holes, even though the holes themselves remain invisible. One of the most dramatic confirmations of black holes came in 2019, when the Event Horizon Telescope collaboration released the first image of a black hole's shadow. By linking radio telescopes across the globe, they created an Earth-sized array capable of resolving details at the heart of galaxy M87. The image showed a bright ring of emission surrounding a dark centre, the shadow of the event horizon. It was not a direct photograph in the usual sense, but a reconstruction from massive amounts of data, yet it was enough to show the predicted shape. The glow was bent light, twisted by space-time into a circle. Seeing that shadow was like glimpsing the edge of time itself, a boundary where our understanding falters. Black holes also play a role in one of the great unsolved puzzles of physics, the information paradox. According to quantum theory, information cannot be destroyed. But if matter falls into a black hole and vanishes at the singularity, what happens to the information it carried? Stephen Hawking famously proposed that black holes radiate energy, now known as Hawking radiation, due to quantum effects near the horizon. Over unimaginable timescales, this radiation would cause a black hole to shrink and eventually evaporate. But if it disappears completely, where does the information go? Is it lost forever, violating quantum principles, or is it somehow encoded in the radiation? The debate continues, with no final resolution yet. Time near black holes is particularly strange. The slowing of clocks in gravity becomes extreme as you approach the horizon. To a distant observer, an object falling in seems to freeze, its time dilated to infinity. To the falling object, time feels normal, but the outside universe seems to speed up, racing forward. This contrast creates some of the most mind-bending scenarios in physics. It suggests that black holes are not just objects but laboratories for exploring the very nature of time. They stretch and distort it in ways that challenge intuition, showing that what feels steady and universal is in fact flexible and fragile. Gravitational waves have given us yet another way to study black holes. When two collide, their violent merger sends ripples through space-time. Detectors on Earth have recorded these waves, confirming not only Einstein's predictions, but also the existence of binary black holes spiraling together. Each detection is a cosmic drumbeat, carrying information about masses, spins, and distances. Listening to these signals is like eavesdropping on the collisions of invisible giants, far away yet powerful enough to shake space-time itself. Black holes also influence their surroundings in quieter ways. At the centres of galaxies, supermassive black holes regulate the growth of stars. When gas falls into them, it can trigger jets and winds that push material outward, preventing too many stars from forming at once. Without this feedback, galaxies might look very different. In this sense, black holes are not just endpoints but organisers of cosmic structure. They help shape the universe, balancing creation and destruction. And yet, despite all we know, black holes remain deeply mysterious. They are places where relativity and quantum mechanics collide, where our best theories clash. They remind us that our understanding of space and time is incomplete, that there are realms where familiar rules break. Each discovery about them answers one question while raising another. Do singularities exist, or are they replaced by new physics? Is information lost, or is it preserved in subtle ways? What happens beyond the horizon, where we cannot see? For you, sitting here and listening, it may feel like these questions are distant abstractions, but in truth, black holes are part of the same fabric of reality you live in. The gravity that keeps you anchored is the same principle that shapes them. The time you measure on your clock is bent by the same equations that govern their horizons. The photons entering your eyes have travelled through a universe sculpted by their presence. They are not exotic outliers, but essential expressions of the same space and time that hold your life. And as we continue to study them, building bigger telescopes, more sensitive detectors, and deeper theories, black holes will keep guiding us toward the edge of understanding. They are not just ends, but beginnings. Not just traps, but teachers. In their shadows lies the promise of deeper insight, reminding us that even in the darkest places the universe continues to whisper its secrets. Every day, without needing to think about it, you move through life with the sense that time flows forward. You wake up, hours pass, the sun shifts across the sky, meals arrive in order, and then night returns. The forward march feels so natural that it rarely invites scrutiny. But when scientists describe the fundamental laws of physics, they find something unsettling. Many of those laws work the same whether time moves forward or backward. Equations describing the motion of particles, the pull of gravity, or the behaviour of electric fields are symmetric. If you rewound the universe in those equations, the math would still hold. Yet your lived experience is nothing like that. You do not see broken cups leap back together, smoke flow back into a candle, or yourself moving from old age to youth. Reality carries an arrow, always pointing one way. The question is why? One of the clearest clues comes from thermodynamics, the study of heat and energy. In the 19th century, scientists like Ludwig Boltzmann developed the concept of entropy, a measure of disorder. The second law of thermodynamics states that in a closed system, entropy tends to increase. Heat flows from hot objects to cold ones, not the reverse. Over time, order decays into disorder. This principle provides a natural direction to time. A shattered glass has more possible arrangements than a whole one, so the universe tends to move towards shattering, not repairing. Smoke disperses because it can spread into far more configurations than it can gather back into a candle flame. Entropy increases, and with it, the arrow of time emerges. This idea explains much of daily experience. You age because the processes in your body are not reversible. Energy spreads, molecules diffuse, and complexity shifts. You can cook an egg, but you cannot uncook it. The path goes only one way. Entropy drives time forward. But this raises a deeper question. If the universe as a whole obeys this law, why was it ever in a state of low entropy to begin with? The arrow of time requires a starting point of unusual order. Cosmologists believe that the early universe after the Big Bang was indeed highly ordered, smooth and uniform, setting the stage for entropy to climb. The origin of that initial condition remains one of the great puzzles. Psychological experience also plays a role in how you sense time's direction. You remember the past, but not the future. Your brain lays down traces of experience, allowing you to recall what has already happened. Without memory, there would be no sense of a flowing arrow, only a continuous present. This asymmetry of memory contributes to the feeling of forward movement. Even if the laws of physics allowed reversibility, the way your mind works locks you into perceiving only one side of the arrow. Causality reinforces this sense. Causes precede effects. You strike a match, and then it ignites. You push a door, and then it opens. If events could happen in reverse order, the world would appear chaotic and incomprehensible. Physics, at its core, does not forbid reversed causality in equations, but in practice, the combination of entropy and quantum probabilities seems to enforce it. The arrow of time is as much about the way events connect as it is about the way energy disperses. On the cosmic scale, the arrow shows itself in expansion. The universe has been stretching since the Big Bang, carrying galaxies apart. This expansion provides a large-scale direction, a past where everything was closer and denser, a future where everything grows farther apart. Just as entropy increases, the cosmos itself evolves along a path that seems irreversible. The microwave background radiation is evidence of that path, a relic of a younger, hotter universe that we can see only behind us, never ahead. Still, scientists sometimes wonder whether the arrow is fundamental or emergent. Could it be that at the deepest level, time has no direction, and the arrow arises only from the collective behaviour of large systems? Boltzmann himself suggested that entropy increase might be a statistical tendency, not an absolute law. If you had a small enough system, entropy might fluctuate, running backward for brief moments. In fact, such fluctuations have been observed in tiny experimental setups where molecules occasionally concentrate rather than disperse. These are rare and fleeting, but they show that the arrow may not be absolute everywhere. It may be a matter of probability, becoming overwhelming only on large scales. Another possibility is that the arrow is tied to cosmology. If the universe has a beginning, then the arrow naturally points away from it. If the universe cycles, expanding and contracting, perhaps arrows could reverse. Some speculative theories imagine multiple universes, each with its own direction of time, or even two halves of one universe with time flowing in opposite directions away from a common origin. These ideas remain untested but show how deep the question runs. In daily life, the arrow of time is inseparable from mortality. You grow older, never younger. Each day moves you forward through the sequence of your life. This is not only biology but physics, the consequence of entropy, memory and causality intertwined. Yet even as it brings limits, the arrow also creates possibility. Without time's direction, there would be no story, no growth, no change. A world where everything happened in reverse or all at once would lack the richness of unfolding. The arrow, in its strictness, gives structure to existence. The strange thing is that in the equations of relativity, time is just another dimension, like space. The block universe picture suggests that past, present and future all exist equally, laid out in spacetime. From that perspective, the arrow is an illusion of perspective, not a fundamental property. Yet your experience tells you otherwise. You cannot step into the future the way you step into another room. You can only wait for it to arrive. The tension between these views remains unresolved. Are you moving along a line that already exists, or is the line itself being drawn as you go? Quantum mechanics adds yet another layer. At the microscopic level, events unfold in probabilities. The collapse of a wave function appears to introduce irreversibility. Once an observation is made, the system settles into a definite state, and the path forward is set. Some interpretations argue that this collapse creates the arrow of time. Others suggest that all possible outcomes exist simultaneously in a multiverse, and the arrow arises from branching rather than collapse. Either way, quantum theory intertwines with the arrow, hinting that direction may emerge not from the universe's geometry, but from its probabilistic nature. You can test the arrow in small ways even now. Place a drop of ink in water and watch it spread. You will never see the ink spontaneously gather back into a drop. Heat a metal rod on one end and watch the warmth flow along it. You will never see the heat concentrate itself on its own. These everyday irreversibilities are reminders of entropy, the simplest expression of the arrow. They are so ordinary that they almost escape notice, yet they reveal the same principle that governs stars and galaxies. In astronomy, the arrow of time is carved into the life cycles of stars. A star burns hydrogen into helium, releasing energy. Over billions of years, it ages, expands, and eventually dies, scattering heavy elements into space. The ashes enrich future stars and planets. This irreversible sequence is the arrow written in stellar processes. Galaxies themselves evolve, collisions reshaping them in ways that cannot be undone. Cosmic history unfolds forward, one step at a time. Even black holes, which seem to defy understanding, follow an arrow. Hawking radiation implies that they slowly evaporate, a one-way path toward disappearance. The growth of entropy in this process is enormous, binding the arrow tightly to the most extreme objects in the universe. If information is preserved, it must be scrambled beyond recognition, yet still consistent with a forward direction. If information is lost, the paradox deepens, but the one-way flow remains. For you, sitting here, the arrow of time is not just abstract. It is in your heartbeat, your breath, your memory of earlier moments. It is in the way you can recall what was said before, but not what will be said next. It is in the way your body changes with age, in the way your days accumulate. The arrow points forward not just in the stars, but in your own experience, linking you with the same principles that shape galaxies. And yet, the mystery remains unsolved. Why was the universe's beginning so ordered? Why do the fundamental equations not show direction, while experience insists on it? Why do memory, causality, and entropy align in the same way? These are questions that touch both physics and philosophy, both the external cosmos and the internal mind. The arrow of time is perhaps the most intimate mystery, because you live it every moment, and yet it resists simple explanation. The journey to understand it continues. Physicists measure entropy in tiny systems, map the cosmic microwave background, test quantum processes, and search for new theories. Philosophers debate whether the arrow is fundamental or emergent. Psychologists study how memory and perception weave time into consciousness. Each perspective adds a piece, but none yet gives the whole. The arrow continues to point, carrying you forward, carrying stars forward, carrying the universe forward, whether or not you understand its origin. And as you listen now, aware of seconds passing, aware of the words unfolding one after another, you're experiencing the arrow directly. It is the invisible current carrying you, unstoppable and universal, yet still a mystery at its heart. Wherever it comes from, whatever it means, it continues, guiding you onward into what comes next. When scientists talk about space and time on everyday scales, the language of relativity works beautifully. Einstein's equations describe the bending of space-time around planets and stars, the slowing of time near black holes, the stretching of the cosmos itself. But shrink down to the smallest scales, to the world of atoms and particles, and a very different set of rules begins to take over. Here, quantum mechanics dominates, and with it comes uncertainty, probability, and puzzles that unsettle even the most confident frameworks. At these scales, space and time do not behave like smooth, continuous fabrics. They shimmer with unpredictability, hinting that the reality beneath the surface may be stranger than either relativity or common sense allows. Quantum mechanics was born in the early 20th century, just as relativity was reshaping the cosmic picture. Physicists studying atoms discovered that classical laws could not explain their behavior. Electrons did not orbit nuclei like tiny planets circling a sun. Instead, they occupied discrete energy levels, jumping between them in ways that defied classical physics. Light was not just a wave, but also behaved like particles, quanta of energy called photons. These discoveries forced a new description of the microscopic world, one built not on certainty but on probability. At the heart of quantum mechanics lies the uncertainty principle. Proposed by Werner Heisenberg, it states that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. The more closely you pin down where a particle is, the less precisely you can know how fast it is moving. This is not a flaw in measurement, but a fundamental property of nature. The very concept of a particle's location becomes fuzzy, described by a wave function that gives probabilities rather than definite answers. This fuzziness complicates how we think about space and time. In classical physics, you can always imagine a particle following a trajectory through space, ticking through time step by step. In quantum mechanics, there is no clear path until a measurement is made. Particles exist in superpositions, spread across possibilities, collapsing into definite states only when observed. Between observations, the concept of position becomes abstract. Space is no longer a stage where particles move like actors. It is part of a probabilistic story where existence itself is blurred. time in quantum mechanics is even stranger. In the Schrödinger equation, which governs how wave functions evolve, time appears as an external parameter, flowing smoothly in the background. But if space and time are supposed to be part of the same fabric, as relativity insists, why does quantum mechanics treat time differently? Space is represented by operators that can be uncertain, but time is treated as absolute. This asymmetry has troubled physicists for decades. It suggests that our theories are incomplete, that space and time are not yet being described in a unified way. Attempts to reconcile relativity and quantum mechanics often run into this conflict. Relativity describes space-time as continuous and geometric. Quantum mechanics reveals discreteness and probability. When you try to apply both at once, say, inside a black hole or at the very beginning of the universe, the mathematics breaks down. Curvature goes to infinity. Probabilities lose coherence, and predictions stop making sense. These failures hint at a deeper theory waiting to be discovered, one that can describe space and time consistently at all scales. One proposal is that space and time themselves may be quantized. Just as matter is made of atoms and energy comes in quanta, perhaps space-time is built from tiny discrete units. At scales near the Planck length, about 10 or 35 meters, the smooth fabric might give way to a granular structure like pixels forming an image. At those scales, the very notion of distance or duration may dissolve. Instead of continuous geometry, reality may be stitched together from quantum bits of space-time, beyond current experimental reach, but essential for a complete picture. The idea of space-time quantization leads to fascinating models. Loop quantum gravity, for instance, suggests that space is woven from networks of loops, with areas and volumes quantized like energy levels in atoms. String theory proposes that particles are not points but vibrating strings, their vibrations giving rise to mass, charge, and force. In string theory, extra dimensions beyond the familiar 3 of space and 1 of time may curl up so small that we cannot perceive them, hidden yet influential. Both approaches aim to describe space-time at tiny scales, though neither has yet been experimentally confirmed. Quantum mechanics also introduces entanglement, a phenomenon Einstein himself called spooky action at a distance. When particles become entangled, their properties link so that measuring one instantly affects the other, no matter how far apart they are. This raises questions about the nature of space itself. If information can connect particles across vast distances instantly, is space really the fundamental medium we think it is? Some researchers now speculate that space-time itself may emerge from patterns of quantum entanglement, that geometry and distance are not primary, but consequences of deeper connections. In this view, space is not a backdrop, but a product of quantum information. Time, too, might be emergent. Some approaches suggest that at the most fundamental level, reality may be timeless. Equations in certain formulations of quantum gravity lack a time variable altogether. Instead, what we perceive as time could arise from correlations between states, from the way changes are recorded in memory or in entropy. Time might be a construct of perspective, not a universal ingredient. If so, then the arrow of time, the flow you feel every second, may be a macroscopic illusion built from microscopic timelessness. Experiments continue to probe these mysteries. Physicists cool atoms to near absolute zero, creating quantum states that stretch across space. They fire particles through double slits, watching interference patterns that reveal wave-particle duality. They measure entanglement across increasing distances, testing whether space-time itself respects or emerges from quantum rules. These delicate experiments inch closer to the frontier where space and time as we know them blur into puzzles. For you, listening here, it may seem far removed. Yet every piece of technology around you depends on quantum rules. The semiconductor in your phone, the laser in a DVD player, the superconducting magnets in MRI machines, all exploit the quantum world. GPS too relies on relativity corrections mixed with quantum timing. Every time you flip a switch or send a signal, you are using the results of these theories, even if the underlying mysteries remain unresolved. The puzzles of space and time at tiny scales are not just curiosities, but the foundations of modern life. And still, the deeper questions persist. Is space-time continuous or discrete? Is time fundamental or emergent? Are there extra dimensions curled beyond our reach? Do singularities point to missing physics, or to the limits of our imagination? Each possibility leads to more questions, weaving a puzzle that grows richer the more we study it. What makes this puzzle so compelling is that it sits at the boundary of knowledge. Relativity works on the large scale, quantum mechanics on the small, but together they clash. Somewhere in that clash lies the path to a more complete understanding. Perhaps space and time, as we currently imagine them, are not the deepest layers of reality. Perhaps they are approximations, like the way air seems smooth until you notice its molecules. Beneath the apparent continuum, a more granular structure may wait, waiting for tools and theories subtle enough to reveal it. The atoms in your body, the bonds that hold them, the photons that let you see, all follow quantum rules. The puzzles of space and time at tiny scales are not elsewhere. They are here, in every interaction, in every breath. They shape your world even as they remain hidden, a reminder that reality is layered and that the most familiar experiences rest on mysteries that still defy full explanation. When most people imagine physics, they picture equations that describe how things move and change over time. A ball rolls down a hill, a planet circles a star, a pendulum swings back and forth. Time feels like the natural parameter tying these motions together, the backdrop against which events unfold. But when you look more closely at some of the deepest equations in physics, you find something surprising. Time is not always there. In fact, some of the most fundamental mathematical descriptions of the universe leave the clock out altogether. They describe states, relationships, and symmetries without mentioning a ticking arrow. This raises a disquieting question. If the universe at its most basic level can be written without time, then what is time really? One of the clearest examples comes from quantum gravity. When physicists try to merge general relativity with quantum mechanics, they often encounter what is called the Wheeler-DeWitt equation. This equation is sometimes described as the quantum version of Einstein's equations, an attempt to unify the geometry of spacetime with quantum principles. But in its most striking form, the Wheeler-DeWitt equation has no time variable. It is timeless. It describes the universe as a whole in terms of possible states, but there is no external clock moving them forward. To many this is unsettling. How can an equation meant to describe everything leave out something as basic as time? Part of the difficulty lies in perspective. In everyday life, we take time for granted because we are immersed in it. We measure it with watches, we remember the past, we anticipate the future. But in physics, what matters are the relationships between states. If you describe the whole universe at once, there is nothing outside it to measure time against. There is no external observer with a stopwatch. Time, in this sense, may not be fundamental. It may be a feature that emerges when you look at subsystems rather than the whole. Julian Barber, a physicist who has spent much of his career thinking about timelessness, argues that what we call time is simply the order of change. According to this view, the universe does not evolve through time. Instead, it consists of a series of possible configurations which he calls nows. The sense of flow comes from the way these configurations are arranged and how they contain traces of one another. Your memory of the past, for instance, is just information encoded in the present configuration. You feel time because one now contains evidence of others. But in the equations, there is no need for an external ticking. The universe just is, in all its possible arrangements. This perspective ties closely to the block universe idea from relativity, where past, present, and future all exist equally. In that picture, time is a dimension like space, and the whole of spacetime is laid out. Motion and change are parsed through that structure, not a universal flow. From within, you feel time passing. From outside, there is no passing, only the totality of spacetime. The timeless equations reflect this by describing the structure as a whole without needing a moving parameter. Quantum mechanics adds more complexity. The Schrödinger equation, which governs the evolution of wave functions, does contain time as a parameter. But in attempts to merge quantum theory with gravity, time disappears again. The Wheeler-DeWitt equation is a direct example of this. Some researchers believe this tension shows that our understanding is incomplete. Others argue that it points to a deeper truth. Time is not fundamental, only emergent. Emergent time means that at the most basic level, the universe does not need a clock. Instead, time arises when parts of the system are compared. Imagine two subsystems within the universe. One can serve as a clock relative to the other. Their correlations create the appearance of temporal flow. Carlo Rovelli, a physicist known for loop quantum gravity, emphasizes this idea. He suggests that time is relational, not absolute. We experience it because we measure change against change. Without comparison, there is no time. This becomes clearer if you think about timeless games. Consider a chessboard. At any given moment, the arrangement of pieces captures a state. There is no time variable in the arrangement itself. The sense of progression comes from comparing one arrangement to another, from remembering previous moves and anticipating future ones. The rules connect the states, but the states themselves are timeless snapshots. Some physicists believe the universe may be similar. The equations describe all possible states, but the flow we feel comes from how those states are connected in experience. The absence of time in some fundamental equations has practical implications. If time is not fundamental, then the arrow of time must emerge from other features, such as entropy or quantum entanglement. It means that the flow you live by may be more like a secondary story, layered on top of timeless mathematics. This does not make your experience any less real, but it changes what we mean by real. Time may not be a basic ingredient of the cosmos. It may be an emergent property of how information and matter interact. This also complicates the way we think about beginnings. If the universe is timeless at its foundation, then the Big Bang is not a moment in time but a boundary of sorts, a condition within the larger structure. Asking what came before the Big Bang may then be a meaningless question, because before presumes time. Instead, the universe may simply be, in its entirety, with what we call the past and the future, both contained within a timeless whole. Still, for practical science, time remains a useful tool. Equations with time parameters describe experiments, predict particle interactions, and calculate orbits. Engineers and scientists rely on these equations daily. The timeless perspective does not erase those successes. Instead, it suggests that time in those contexts is approximate, a convenient way of describing correlations. On deeper levels, the correlations themselves may not require an external clock. The idea that time could be absent also touches on philosophy. If the universe is timeless, then the flow of your life is not something written into the cosmos, but something created by consciousness. Memory, perception, and entropy align to give the sensation of movement from past to future. Without minds to notice, perhaps there would be no sense of time at all. Or perhaps time exists only as a relational property of physical states, independent of observation, but still not fundamental. Experiments continue to explore these questions. Quantum simulations test how entanglement can create effective time. Theoretical models examine how the arrow of time emerges from correlations. Cosmologists analyze whether timeless descriptions of the universe can explain observations of expansion and structure. So far, no definitive answer has emerged, but the very fact that equations can describe reality without time shows how much we have yet to understand. The ticking clock on your wall, the heartbeat in your chest, the memory of moments already lived. These are expressions of time as you know it. Yet underneath, the equations describing atoms, fields, and space-time itself may not need that ticking. The paradox is that your most constant experience may be an emergent story told by a universe that, at its deepest level, has no clock at all. When you think about your life, it feels natural to imagine it unfolding in time. One moment follows another, and the story builds. Birth, growth, memory, and anticipation all depend on this sense of movement. Time feels as real as the ground beneath your feet. Yet when physicists and philosophers dig deeper, they sometimes wonder if time might not be as fundamental as it seems. Perhaps time is not a basic ingredient of the universe, but something that emerges from deeper structures. If that is true, then the flow you experience could be an illusion, a story constructed by your mind and by the laws of physics working together. The idea of emergent time begins with a simple observation. Many of the equations describing the universe do not need time. They describe states and relations between states without invoking a ticking clock. In these equations, there is no universal now, advancing from one moment to the next. There are only configurations connected by rules. From this perspective, time might not be woven into the fabric of reality. Instead, it could arise the way temperature arises in physics. Temperature does not exist at the level of individual molecules. Each molecule has energy and motion, but temperature is a property that emerges when many molecules interact. Perhaps time is similar. Not a fundamental thing, but a large-scale property that appears when matter, energy, and information interact in complex ways. One place this idea becomes vivid is in quantum entanglement. When particles become entangled, their states are linked no matter how far apart they travel. Some researchers suggest that the geometry of space-time itself may emerge from patterns of entanglement. If that is true, then space and time are not fundamental frameworks, but products of deeper quantum relationships. They appear solid and continuous only because we observe them at large scales, just as a surface of water appears smooth even though it is made of countless molecules in motion. In this view, time is a kind of effective description, arising from the correlations between states rather than existing independently. Another clue comes from the way memory works. Your brain does not record continuous time. It stores snapshots, traces of events, and strings them together. The sense of flow is constructed from those memories and from the anticipation of what might come next. If you had no memory, you would not experience a past, and if you had no capacity to imagine, you would not anticipate a future. You would simply exist in an ongoing present. That suggests that part of what makes time feel real is psychological. Consciousness stitches experiences together into a narrative, creating the illusion of motion through time. Entropy also plays a role in this illusion. As disorder increases, you perceive direction. Ice melts, but water does not freeze spontaneously without outside help. Smoke spreads, but it does not gather. These processes provide an arrow that your mind interprets as flow. Without entropy increasing, the distinction between past and future would blur. This means that time's direction could be a byproduct of thermodynamics, not a fundamental feature of the universe. If entropy were absent, perhaps time itself would lose meaning. Experiments in physics reinforce this idea. In small quantum systems, where fluctuations dominate, entropy can decrease for short intervals. In such cases, the arrow of time seems to waver. On very tiny scales, time might not behave the way it does in your everyday life. Only when many systems are combined, smoothing out the fluctuations, does the arrow become strong and consistent. This supports the notion that time emerges statistically, not absolutely. Some physicists go further, suggesting that the universe as a whole may be timeless. The equations describe a set of possible states, and what we call time is simply the order in which those states appear to us. Julian Barber, for example, argues that the universe consists of a collection of nows, timeless configurations that contain traces of one another. Our sense of continuity is built from those traces, not from an external river. In that picture there is no true flow. The universe just is, and time is the story we tell as we move from one configuration to another. This can feel unsettling, because your intuition insists that time is real. You feel it passing with every heartbeat, every glance at a clock. But consider that many other sensations are also illusions of construction. Colour, for instance, is not an objective property of light, but a way your brain interprets wavelengths. Sound is not inherent in air vibrations, but arises from the way your ears and brain process them. Perhaps time is similar, an emergent feature of perception layered on top of physical processes. In cosmology, the idea of emergent time becomes even more intriguing. If the universe began in a hot, dense state, then time as we know it may not have existed before that. The early universe might have been governed by quantum conditions where time had no meaning. Only as it expanded and cooled, creating entropy and structure, did time emerge as a useful description. Asking what happened before the Big Bang might therefore be meaningless. There may not have been a before at all, only a timeless quantum state from which our familiar time unfolded. This does not make time less important for your life. Even if it is emergent, it governs everything you do. Clocks still tick, memories still accumulate, and futures still unfold. But it does mean that the deepest levels of physics may not include time in the way you imagine. Instead, time may be a useful approximation, like a map that works well at certain scales but not at others. Beneath it lies something more fundamental waiting to be described. One challenge in thinking about emergent time is language. Our words and grammar are soaked with temporal ideas. We speak of past, present, and future, of before and after. To imagine a world without time is almost impossible because our thoughts are framed within it. Yet mathematics offers a way around this. Equations can describe states without invoking flow. They can capture structure and relation without ticking. It is through this abstract language that physicists try to peer past the illusion, searching for the deeper order from which time arises. Experiments continue to probe this possibility. Quantum simulations explore whether time can emerge from entanglement. Cosmological models test whether expansion and entropy can create the arrow. Physicists examine whether timeless equations can still reproduce the predictions of ordinary quantum mechanics. Each step brings hints, though no final answers. The idea that time could be emergent remains speculative, but it is taken seriously because it explains why some equations do not require it, and why others treat it differently than space. For you, sitting here, it may be enough to reflect that the sense of flow you feel is not as straightforward as it seems. It could be that time is not an underlying ingredient of the universe, but a phenomenon rising from relationships, correlations, and memory. The seconds on your watch are real for you, but at the most basic level, the universe may not contain seconds at all. Instead, it may contain only configurations, stitched into a story by entropy, physics, and consciousness working together. If time is emergent, then the universe is stranger than you might have imagined. It means that one of your most basic intuitions, the forward march you feel every day, is not built into the fabric of existence. It is built from deeper patterns, hidden yet powerful, shaping everything from the ticking of a clock to the unfolding of galaxies. And if that is true, then exploring time is not just about studying motion or memory. It is about peeling back layers of reality to see how the story itself is told. When you think about your own life, it feels like you are moving through time. Each second arrives, is lived, and then is gone, carried into memory as you continue forward into the next. The sense of a moving present is so deeply ingrained that it seems unquestionable. Yet one of the most striking interpretations of relativity suggests a very different picture. Instead of flowing, time may be laid out all at once, a dimension like space, where every past, present, and future event exists simultaneously. This perspective is called the block universe, and it turns the way you normally think about existence inside out. The origins of this view go back to Einstein's theory of relativity. In Newton's world, time was absolute, flowing uniformly everywhere, the same for all observers, but relativity showed that simultaneity is relative. Two events that appear simultaneous to you may not be simultaneous to someone moving at a different speed. There is no universal now that all observers share. This shatters the idea of a global present and replaces it with something more subtle. Each observer has their own slice of space-time, defined by motion and perspective. If there is no single present moment shared across the cosmos, then perhaps all moments exist equally. Imagine space as a landscape. You can walk north, south, east, or west, and every point already exists whether you're standing on it or not. In the block universe, time is like that too. The moment of your birth, this very moment now, and moments still to come are all points in the four-dimensional block of space-time. You're not moving through time, you're extended in it, like a long object stretched across the temporal dimension. From your perspective, you feel yourself moving, but from the perspective of the block, all of you already exists. This can feel strange, because it conflicts with the everyday sense of becoming. If all moments exist, then the future is already there. The idea of choice or change seems to dissolve, yet relativity strongly supports this picture. The lack of a universal present suggests that the distinction between past, present, and future may be an illusion of perspective, not a feature of reality itself. What you call now is simply the slice of space-time you are currently experiencing. But the block as a whole does not privilege one slice over another. Philosophers and physicists have debated this view for decades. Supporters argue that it makes sense of relativity and explains why equations do not require a flowing time. Detractors argue that it undermines free will and conflicts with the way we experience life. The debate touches not only physics but also metaphysics, psychology, and even ethics. If all moments exist, then in some sense, your childhood is still happening, your old age is already real, and everything in between is fixed. Your story is not being written as you live it. It is already written, and you are reading through it one line at a time. This does not mean you are powerless or that choices are meaningless. From within the block, your decisions are part of the structure, shaping the future in the same way your actions shape the present. The sense of choice is real, but it is contained within the larger geometry of space-time. Your agency is not erased. It is part of the block itself, a thread woven through it. The paradox arises only if you imagine time as flowing like a river. If instead you imagine it as a dimension, then your actions are simply coordinates within it, as real as your location in space. The block universe also changes how we think about death and memory. If every moment exists equally, then the past is not gone. It is still part of the block, as real as the present. The people you remember, the events that shaped you, are still there in space-time, even if you can no longer reach them. This perspective can be comforting or unsettling, depending on how you look at it. It suggests that nothing is ever truly lost. It also suggests that what you fear as the future is already laid out, unchangeable. Whether this feels liberating or confining depends on how you interpret existence within the block. Experiments in relativity strengthen the case. Time dilation, observed in fast-moving particles and precise atomic clocks, shows that different observers truly experience different flows of time. One person's hour is another's 2 hours, yet both are equally valid. There is no master clock. This supports the idea that time is not a universal flow, but a dimension experienced differently depending on perspective. The block universe takes this to its logical conclusion. All events exist, and your motion through them is relative. Critics of the block universe argue that it denies the reality of becoming. They point out that our experience of novelty, surprise, and change is too central to dismiss as illusion. They also argue that if the future already exists, then free will is compromised. Why bother making choices if the outcome is already fixed? Supporters reply that choice is simply how the block looks from within. The future exists, but it exists as shaped by your choices. Both determinism and agency can coexist in this geometry. There are also alternatives to the block. Some interpretations propose that only the present is real, a view called presentism. Others suggest that the past and present are real, but the future is not, a view called the growing block. These models preserve a sense of becoming, but conflict with relativity's rejection of universal simultaneity. The block universe remains the cleanest fit to relativity, even if it challenges intuition. For you, living inside your own story, the block universe may sound abstract, yet it affects how you see yourself. If all of your life exists, then your present moment is one of many frames in a larger film. You're not moving through time. You're the film itself, with every frame equally real. What feels like motion is the way consciousness reads through the strip. This does not make your experiences less real. It means they are part of a larger whole that does not vanish when the frame changes. Quantum mechanics complicates this picture. Some interpretations suggest that all possible futures exist in branching universes, creating a multiverse rather than a single block. In that case, the block may not be fixed but branching, with many possible paths coexisting. Other interpretations argue that even in quantum theory, the block remains intact, with probabilities embedded in its structure. The debate continues, and it may be that neither picture is complete. Still, the block universe is one of the most radical ideas to come from relativity, because it challenges the most basic intuition, that time flows. It replaces flow with geometry, becoming with being, change with structure. Whether this is ultimate reality or only an approximation remains unknown, but it shows how deeply relativity reshapes our sense of existence. And as you reflect on this, you may realize that even now, the words you're hearing are not just unfolding, but already part of a larger whole. This moment, the memory of moments past, and the anticipation of moments yet to come may all coexist in the same block. You experience them in sequence, but sequence may not be fundamental. It may be perspective, a way of reading through something that already exists. The block universe suggests that reality is not a story being told, but a story already written, and you are both the reader and the character within it. When you think about the universe, it is tempting to imagine it as everything there is. The word itself almost demands it. Universe, a single whole, all that exists. Yet the more physics explores the nature of space and time, the more seriously scientists consider the possibility that what we call the universe might be only one piece of a larger structure. There could be other universes beyond our own, realms with their own space, their own time, their own versions of what is possible. And alongside these physical possibilities sits another equally striking idea from quantum mechanics: that reality itself may branch into multiple versions every time a choice is made. Together, these ideas create a picture where there may not be one single now, but countless nows, unfolding in parallel, layered upon one another in ways that challenge the very meaning of reality. The thought of multiple universes has roots both in cosmology and in quantum physics. From the cosmological side, inflation theory provides one path. Inflation suggests that in the earliest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, stretching space faster than the speed of light. This expansion smoothed out the cosmos and set the stage for galaxies to form. But inflation may not have ended everywhere at once. Some versions of the theory predict that inflation continues in other regions, spawning bubble universes beyond our observable horizon. Each bubble could have its own laws of physics, its own constants, perhaps even dimensions beyond those we know. From within, each bubble appears as a universe in its own right, unaware of the others. This eternal inflation scenario turns the word universe into one local patch of a multiverse far larger than anything you can see. From the quantum side comes the many worlds interpretation. Quantum mechanics describes particles not as having definite properties, but as existing in superpositions, clouds of probabilities. When you measure a system, it seems to collapse into a definite outcome. But what if the wave function never collapses? What if every possible outcome actually happens, each in a different branch of reality? This is the idea of many worlds, proposed by Hugh Everett in the 1950s. In this view, every quantum event splits reality into multiple versions. You choose to turn left, and in another branch you turn right. You flip a coin, and both heads and tails exist in different branches. All possibilities are realized, each in its own world. These two visions, the cosmological multiverse and the quantum many worlds, are not the same, but they share a common theme. They both suggest that reality is larger than what you directly experience. Your now may be one of countless nows, unfolding in parallel or scattered across infinite bubbles. The idea can feel dizzying, because it challenges the uniqueness of experience. Are you one version among many? Are your choices truly yours, or are they simply one branch among all possible branches? Philosophically, this raises profound questions. If every outcome exists somewhere, then what does it mean to make a choice? From your perspective, choice is real, because you experience only one branch. But in the larger structure, every choice is realized. This does not erase agency, but it reframes it. Your actions still shape your reality, but they also coexist with other versions shaped by other choices. In many worlds, you're both unique and multiplied, one thread in a vast tapestry of branching possibilities. Cosmologically, the multiverse raises its own puzzles. If there are infinite universes, each with different laws of physics, then perhaps our own is simply one where the conditions happen to allow life. This is sometimes called the anthropic principle. Out of countless possibilities, you find yourself in a universe that permits your existence, because you could not exist in one that did not. This explanation feels unsatisfying to some, because it replaces a why with a because we are here. Yet it remains one of the ways physicists grapple with why the constants of nature seem so finely tuned. Evidence for other universes is difficult to obtain, because by definition they lie beyond what we can observe. Yet subtle clues might exist. Collisions between bubble universes, if they ever occurred, could leave imprints in the cosmic microwave background. Researchers have searched for such patterns, though none have been confirmed. In quantum mechanics, many worlds produces the same predictions as standard interpretations, making it hard to test directly. Critics argue that without empirical evidence, these ideas remain speculative. Supporters counter that they provide consistent explanations for puzzles otherwise left unresolved. For you, thinking about many nows, the implications stretch beyond science. If the block universe suggests that all moments exist equally, many worlds adds another layer. All possible moments exist too. Your life may not be a single path through time, but a branching tree, with versions of you walking down every possible corridor. Each version feels real, because within its branch, it is real. From outside, if such an outside exists, all the branches coexist. The self you know is one among many, each shaped by different outcomes. This idea can feel overwhelming, but it can also be strangely grounding. If all possibilities exist, then your experience is still unique. You inhabit one branch, one world, one bubble. The others may exist, but they do not change the reality you live in. Your choices still matter to you. Your now is still yours. The multiverse does not erase meaning. It reframes it in a larger context, one where meaning is local and personal rather than universal. Some thinkers even speculate that consciousness itself may play a role in selecting among branches. This is controversial and far from proven, but it reflects the deep unease many feel about a purely branching reality. Does awareness collapse possibilities, or does it simply ride one of the branches? Quantum mechanics leaves the question open. The multiverse offers one answer. All branches happen with or without observation. Consciousness does not collapse them. It simply experiences one. The concept of many nows also connects to the nature of memory and anticipation. You remember one past, not many, and you anticipate one future, not all. This makes your branch feel singular, even if others exist. The illusion of uniqueness may be part of what gives life coherence. If you were aware of multiple nows, overlapping and diverging, the sense of continuity would break. Perhaps this is why experience is limited to one branch at a time. It allows you to live with meaning and focus, even if the multiverse sprawls invisibly beyond. Speculative theories even imagine that universes might interact, that information might leak between branches or bubbles. Some models of quantum gravity hint at wormholes connecting different regions, or at entanglement weaving together separate realities. These remain speculative, but they show how far the idea of many now stretches, challenging every intuition about what existence means. For everyday life, though, what matters most is the now you are in. Whether or not other nows exist, your experiences are tied to this one, this branch, this bubble, the sound of a voice, the beating of your heart, the memory of a moment past. These are your anchors. They connect you to the reality you inhabit. If other realities exist, they are not yours. The multiverse may be vast, but your now is still singular in meaning. And yet, the thought that there could be many nows lingers. It reshapes how you think about beginnings, endings, choices, and chance. It invites you to imagine a reality larger than the one you see, where the concept of a single universe is only a fraction of what exists. Whether or not it's true, the idea expands your perspective, reminding you that the boundaries of space and time may not be as firm as they seem. When you think about space and time, your mind often goes outward to the universe, to stars, to galaxies, to physics that stretches across unimaginable scales. But just as profound is the way space and time live inside you. Every breath you take, every beat of your heart, every cycle of waking and sleeping is a rhythm, a marking of time not by clocks on the wall, but by processes deep in your cells. You're not separate from time. You're a creature built from it, regulated by it, synchronized to it in ways both subtle and powerful. The story of time is not only written in cosmic expansion or black holes, it is written in your body, in the cycles that make life possible. Your first awareness of time likely came not from a clock, but from your body's rhythms. Hunger comes in waves, sleepiness gathers at night, alertness rises with the morning. These patterns are so natural that you rarely question them, yet scientists have learned that they are the result of finely tuned biological clocks ticking inside nearly every cell. These clocks do not measure seconds the way a wristwatch does. Instead, they keep track of cycles, oscillations that repeat daily, monthly, or yearly. Collectively, these cycles are called biological rhythms, and they are the ways life has adapted to the rhythms of Earth itself. The most familiar of these is the circadian rhythm, the roughly 24-hour cycle that governs sleep and wakefulness, hormone release, body temperature, and countless other processes. Circadian rhythms are tied to the rotation of the Earth, to the cycle of light and darkness that repeats each day. In humans, a region of the brain called the suprachiasmatic nucleus acts as a master clock, synchronizing rhythms across the body. Light entering your eyes helps reset this clock each morning, anchoring you to the day-night cycle. Without this anchor, your rhythm would drift, free-running slightly longer than 24 hours. These rhythms are not superficial. They reach into metabolism, immune function, and cognition. Disrupt them, and you feel it immediately. Jet lag is a simple example. When you cross time zones, your circadian rhythm lags behind the new environment. You feel tired at odd hours, hungry at the wrong times, unable to concentrate. Shift workers face a more chronic version of this, forced to stay awake at night and sleep in the day, fighting against biology's natural clock. Over time, these disruptions can affect health, showing how deeply time is woven into physiology. But circadian rhythms are not the only biological cycles. There are ultradian rhythms, shorter than a day, such as the 90-minute cycles of REM and non-REM sleep. During the night, your brain and body cycle repeatedly through stages, from deep, slow-wave sleep to vivid dreaming and back again. These cycles shape not just rest, but memory, emotion, and learning. Even in waking hours, your body shows ultradian fluctuations in attention, alertness, and hormone release. There are also infradian rhythms, longer than a day. Menstrual cycles in humans are one example, tied to hormonal oscillations that repeat monthly. Seasonal rhythms too affect animals and plants, guiding migration, hibernation, flowering, and breeding. These cycles are tied to Earth's orbit around the Sun, to the yearly changes in light and temperature. Even when removed from external cues, many organisms continue to show these rhythms, revealing internal clocks that anticipate the environment rather than just reacting to it. The existence of these rhythms shows how life has adapted to the spacetime of Earth. The planet spins once every 24 hours, orbits the Sun once a year, and tilts to create seasons. Organisms evolved within these cycles, internalizing them so deeply that they became biology itself. Your body is not just in time, it is of time, a product of cosmic rhythms made flesh. The molecular machinery behind these rhythms is intricate. Inside cells, feedback loops of gene expression and protein interactions create oscillations. Certain genes turn on and off in cycles, producing proteins that regulate their own expression. These loops create the ticking of cellular clocks. In the brain, neurons of the suprachiasmatic nucleus coordinate these cycles, aligning them with light signals. Across tissues, peripheral clocks keep local time, orchestrating metabolism in the liver, muscle function, and countless other processes. Together, these clocks maintain harmony, like instruments in an orchestra playing in synchrony. Understanding these rhythms has practical importance. Medicine now recognizes that the timing of treatments can matter as much as the treatment itself. This field, called chronotherapy, studies how drugs interact with biological clocks. Some medications are more effective or less toxic if taken at specific times of day, aligned with rhythms in hormone levels, metabolism, or cell division. Cancer therapies, for instance, may exploit the timing of cell cycles. Even blood pressure medications can work better if timed to match daily fluctuations. Athletic performance, too, is influenced by biological rhythms. Strength, flexibility, and endurance vary across the day, tied to body temperature and hormone cycles. Cognitive performance follows patterns as well, with attention and memory peaking at certain hours. These variations remind us that you are never separate from time. It shapes your abilities moment by moment. Sleep is perhaps the clearest expression of time inside you. Each night your brain cycles through patterns of activity, consolidating memories, regulating emotions, and repairing tissues. Disrupt sleep, and your sense of time itself can warp. Hours stretch or collapse, days blur together, and even reality can feel unstable. Sleep deprivation experiments show how essential these nightly rhythms are, not only for health, but for a coherent sense of self. Without them, the flow of time within you falters. On evolutionary scales, these rhythms connect life to the cosmos. Ancient cyanobacteria, among the earliest photosynthetic organisms, evolved circadian clocks billions of years ago to optimize light harvesting. These clocks still influence descendants across the tree of life. Migration of birds, breeding cycles of mammals, flowering of plants, all attuned to astronomical cycles. The rhythms of life are echoes of Earth's rotation and orbit, imprinted in DNA. Even shorter cycles like heartbeats reveal temporal structure. The heart does not beat randomly. It follows rhythms tuned by electrical signals and feedback loops. Breathing too oscillates, synchronized with activity and rest. These cycles scale upward, combining with circadian and seasonal rhythms to create the temporal architecture of life. Every system in your body is timed, layered, interwoven. Yet these rhythms are not rigid. They can adapt to new environments, reset by cues like light, food, or temperature. This flexibility allows life to survive across latitudes, climates, and changes. It shows that biological time is not absolute but relational, tied to space and environment. In this sense, your body reflects the same principle seen in relativity. Time is not one thing everywhere, but a relationship between system and context. For you personally, being aware of these rhythms can change how you live. Noticing when you are naturally most alert or when rest comes easiest allows you to align with your own internal clocks. Paying attention to light exposure, meal timing, and sleep patterns can improve well-being because they respect the temporal structure built into your body. Time is not just on the clock, it is in your cells, in your brain, in every beat and breath. Thinking about biological rhythms reminds you that time is not only cosmic but intimate. It is not only about galaxies drifting or black holes bending. It is about the cycles that sustain you, the invisible clocks that make life possible. You are a rhythm within larger rhythms, a living expression of space and time folded inward. And as you reflect on this, you may begin to sense that the story of time is not just out there in the stars, but also here, beating quietly inside you, guiding you onward with every cycle that turns. When you glance at a clock, the numbers and hands seem to give an objective account of time. Minutes tick away at the same pace for everyone. Hours unfold evenly across the day, and the rhythm feels impartial, detached from human experience. Yet the way you actually feel time passing is far less steady. A minute in boredom can stretch endlessly, while a joyful afternoon vanishes in what seems like a blink. Days can feel heavy and long, and then months disappear in retrospect. This difference between measured time and lived time is what psychologists call psychological time, and it reveals that the hours you experience are not simply given by clocks, but shaped by your mind. From the earliest moments of life, your sense of time begins to form through perception. Infants do not yet distinguish sharply between past and future. Their experience is mostly present-centered, with memory and anticipation only slowly developing. As memory grows, so does the ability to perceive duration. A child's wait for a holiday or birthday can feel infinite, because the ability to compare long spans of time has not yet matured. Adults, by contrast, compress such spans because they have lived many more of them. A year in childhood feels vast, while in adulthood it shrinks, one among many already lived. This developmental change shows how psychological time is tied to memory and perspective. Attention is another powerful influence. When you're fully engaged, immersed in a task or in flow, time seems to accelerate. Hours pass unnoticed, and only when you step back do you realize how much has gone by. Conversely, when attention drifts or when you're forced to wait, time slows. The mind marks every passing second because it has little else to occupy it. This connection between attention and perceived duration has been studied in countless experiments. People asked to watch a blank screen consistently overestimate time intervals, while those distracted by engaging tasks underestimate them. Emotion also bends time. Fear, anxiety, and anticipation often stretch moments. Think of the way time seems to crawl in the seconds before an important exam or in the instant before an accident. The brain floods with arousal, processing details more quickly, creating the impression that more time has passed. Joy and excitement, on the other hand, compress time. Vacations end before they seem to have begun. Conversations with friends vanish into memory too quickly. Depression too has its distortions, often making time feel heavy and stagnant, dragging endlessly with little relief. These emotional shifts show that the mind is not a passive receiver of time, but an active interpreter, colouring hours with psychological states. The brain mechanisms behind this are complex. Unlike vision or hearing, there is no single organ dedicated to time. Instead, multiple regions contribute, from the basal ganglia to the cerebellum to the prefrontal cortex. Neural circuits generate oscillations, and these rhythms help measure intervals. Neurotransmitters like dopamine also play a role. When dopamine levels are high, intervals tend to feel shorter. When low, they feel longer. This connection explains why disorders that affect dopamine, such as Parkinson's disease, alter time perception. It also explains why certain drugs, which modulate dopamine, change how people experience duration. Culture further shapes psychological time. In some cultures, punctuality is emphasized, and clocks dominate life. In others, time is treated more fluidly, events unfolding when they are ready rather than at precise moments. These cultural differences affect how individuals experience waiting, planning, and urgency. Even within one society, personal attitudes toward time vary. Some people feel constantly pressed, rushing against deadlines, while others move more at ease, unbothered by the ticking clock. Psychological time is never purely individual. It is learned, reinforced, and shared through social rhythms. Memory distorts time in yet another way. When you look back on life, periods of novelty often seem longer in retrospect. A childhood summer packed with new experiences stretches in memory, while routine adult weeks blur together, compressed into a vague span. Psychologists call this the holiday paradox. Vacations feel short while you're in them, but long when you remember them later. Novelty creates more memories, filling the mental timeline with details. Routine creates fewer markers, making the period seem shorter in hindsight. Thus, the richness of memory reshapes your perception of duration both during and after events. Technology also interacts with psychological time. In a world of constant notifications and digital schedules, attention is fragmented and the pace of life can feel accelerated. People speak of time speeding up in modern life, not because clocks run differently, but because the mind is pulled in many directions. The overload of stimuli compresses perception, leaving little space for spacious, lingering hours. Paradoxically, long exposure to screens can also create time gaps, where hours slip away unnoticed. Both acceleration and disappearance of time are amplified by digital environments, altering psychological rhythms. There are also altered states that transform time more dramatically. Meditation often slows perception, creating a sense of expanded present. Psychedelics can distort time radically, making minutes feel like hours or collapsing hours into a moment. Athletes in peak performance describe losing track of time entirely, existing only in the movement itself. Trauma survivors sometimes report time standing still, a second stretching to infinity under extreme stress. These states show the flexibility of temporal experience, the way the mind can stretch or compress duration depending on context and state of awareness. For daily life, these differences have practical effects. A person who feels time dragging at work may experience stress or dissatisfaction, even if the measured hours are the same as anyone else's. Someone who loses themselves in fulfilling activities feels time flying, which can enhance satisfaction. Managing attention and emotion therefore shapes not just productivity, but the quality of lived time. Psychological time is not a trivial curiosity. It is central to well-being. Aging brings its own shifts. Many older adults report that years pass faster than they once did. Part of this is proportional. Each year is a smaller fraction of a lifetime, but part is also cognitive. With fewer novel experiences, memory lays down fewer markers, compressing decades. Seeking novelty, then, is not just a way to enrich life, but also a way to slow its perceived passage. Engaging in new learning, travel, or relationships fills memory with detail, expanding the mental timeline. Psychological time, unlike clock time, is elastic, shaped by choices and experiences. In neuroscience, researchers study how the brain constructs duration from signals. Some propose an internal clock based on oscillating neurons. Others suggest that time perception emerges from the accumulation of neural activity, like sand piling up in a glass. Still others argue that time is not represented at all, but is simply the order of events encoded in memory. These debates mirror the philosophical debates about physical time, showing how psychology and physics intersect. Just as physicists ask whether time is fundamental or emergent, psychologists ask whether temporal perception is an internal mechanism or a construct layered on other processes. For you, sitting now, this may feel abstract, but you have already experienced it countless times. Think of the way childhood summers seemed endless, or how the last hour of waiting at an airport stretched unbearably, or how an evening with friends ended far too soon. Each of these moments was shaped not by the clock, but by the mind. The same 60 minutes can be an eternity or an instant. The elasticity of psychological time is one of the most intimate ways you interact with the mystery of time itself, and this elasticity connects you again to the larger themes. Just as relativity shows that time flows differently depending on motion and gravity, psychology shows that time flows differently depending on attention, memory, and emotion. In both cases, time is not absolute. It is relative to perspective, context, and state. Whether in physics or in the mind, time is flexible, not rigid. The parallel is striking, a reminder that you are part of the universe's deeper patterns, experiencing them inwardly, even as they shape the cosmos outwardly. When you step back from the theories, the experiments, the puzzles of relativity and quantum mechanics, what remains is the fact that you are living every day inside space and time. These concepts may sound abstract when wrapped in equations and cosmological models, but they are also the most intimate features of your existence. Every breath you take unfolds in time. Every place you inhabit is a location in space. The universe does not only stretch across billions of light years, it stretches into you, shaping the way you move, think, and live. To reflect on space and time is not to leave your daily life behind, but to understand more deeply the stage you're already on. Think for a moment about the space around you. The walls of your room, the floor beneath you, the air filling the gaps. It is easy to treat space as emptiness, as background, but without it, nothing could be. Space allows separation, gives dimension, creates the possibility of arrangement. Objects have meaning only because they occupy positions in space relative to one another. Even your own sense of self is partly spatial. You know where your body ends and where the rest of the world begins. You navigate through doorways, reach for objects, feel the distance between yourself and others. Space is not only out there, it is the framework through which you perceive and engage with reality. Now think about time. You may not always notice its passing in the moment, but it shapes everything you do. You cannot escape it, nor can you hold it. It flows forward, carrying your experiences, your memories, your growth. Every joy you have ever felt is a point in time. Every challenge you have faced is another. Even now, as you listen, time is moving. The words are only possible because one follows another. The sentence is building from past to present to anticipation of what comes next. Time is not just a measure. It is the medium of experience itself. These reflections might sound obvious, yet they remind you that space and time are not distant scientific curiosities. They are the fabric of your life. When you read about galaxies drifting apart or black holes warping space-time, you're not hearing about something entirely alien. You're hearing about principles that also hold you in place, that regulate your heartbeat, that let light reach your eyes. The universe's grand stage is the same one you occupy each day, scaled up from the local to the cosmic. Consider how closely you are tied to rhythms of space and time. The Earth rotates, giving you day and night. It orbits the sun, giving you seasons. The tilt of its axis shifts temperatures and light, influencing everything from crops to moods. You live in step with these rhythms whether you think about them or not. Your body's internal clocks echo them, guiding sleep and wakefulness, hunger and rest, energy and repair. Time is not just measured by clocks. It is encoded in biology, in cycles that link you to the planet and to the cosmos. Your mind, too, is a constructor of time. It strings events into narrative, turns moments into memory, and projects possibilities into the future. Without memory, you would not have a sense of past. Without imagination, you would not have a sense of future. The flow you feel is created in part by this mental stitching. It does not make it less real. It makes it yours, a lived experience shaped by the brain as much as by the universe. And yet, as much as time feels solid, physics reminds us that it is relative. A clock on a mountain ticks faster than a clock at sea level. A satellite circling Earth experiences time differently than you do on the ground. The speed of light, unchanging, demands that time bend to accommodate it. This relativity shows that time is not universal. It depends on motion, on gravity, on position. You live inside one version of it, but there are many stitched together into the larger fabric of space-time. Space too resists simplicity. What feels like empty volume is alive with quantum fields, fluctuations and invisible structure. It bends under mass and energy, carrying light along curved paths, shaping galaxies into clusters, shaping stars into orbits. Even the room you sit in is not truly empty. It is filled with invisible influences, from gravity threading through it to electromagnetic fields bouncing inside it. What looks like nothing is full of something. Reflecting on these ideas can bring humility. The universe is vast beyond comprehension, and the laws that govern it are subtle, often defying intuition. Yet the same laws that guide galaxies also guide you. The same space-time that bends starlight also carries your heartbeat forward. You're not outside the universe looking in. You're part of it, made from its matter, shaped by its rules, sustained by its rhythms. Space and time are not only the backdrop of your story, they are the story. It can also bring comfort. If the block universe is correct, then the moments you cherish are still there, existing in space-time alongside you. If emergent time is correct, then the flow you feel is the result of deeper connections, a tapestry of correlations that make experience possible. If many worlds is correct, then countless versions of you are exploring countless nows. Each idea is strange, but each connects you more deeply to the universe, reminding you that what you call ordinary is built on extraordinary foundations. Your everyday life is full of reminders of this connection. When you check your phone for directions, you're using GPS satellites corrected for relativistic time dilation. When you flip a light switch, photons carry energy across space that is anything but empty. When you breathe, circadian rhythms align your body with the planet's rotation. Even something as simple as watching a sunset ties you to cosmic geometry, to the tilt of Earth and the scattering of light. These ordinary acts are layered with cosmic meaning once you pause to notice them. Living in a space and time means living within limits. You cannot escape gravity. You cannot stop entropy. You cannot step outside of time to see it whole. But it also means living within possibilities. Space allows exploration, creation, connection. Time allows growth, memory, anticipation. The very limits give shape to experience. Without them, life would be formless. With them, it has story and meaning. For you, reflecting gently now, space and time may seem less like abstract puzzles and more like companions. They have always been with you, guiding you silently, surrounding you with structure and flow. The universe you inhabit is not distant but immediate, not alien but intimate. To live is to live in space and time, to carry their mysteries within you as much as around you. And as you sit here, letting these thoughts settle, you may notice that the reflection itself is shaped by the very subject. The words arrive one after another, filling space with sound, carried forward by time. Each sentence is both a moment in space and a moment in time. Together they form not a conclusion but a continuation. A reminder that living in space and time is not something you step outside of. It is the only way you've ever lived, and the only way you ever will, carried gently forward by the same currents that guide galaxies across the sky. As we come to a quiet pause in this journey, the thoughts of space and time may still linger with you. We have wandered across distant galaxies, curved spacetimes, quantum puzzles, and the hidden rhythms within your own body. What began as questions about the cosmos became reflections on the way you live each moment, reminding you that space and time are not far away but woven into everything you do. Every breath you take, every memory you hold, every glance at the sky is already part of this fabric. The ticking of clocks, the shifting of seasons, the flow of your own perception are all expressions of the same reality that bends light and carries galaxies apart. You are not outside of it, looking in. You're within it, carried by it, shaped by it. It is enough for now to rest in that awareness. You do not need to solve the questions or hold on to the details. The mysteries will wait, whether or not you return to them. What matters is the calm sense that you are part of this unfolding story, living within the same currents of space and time that guide stars and planets. And as the words fade, time continues quietly, carrying you onward into the next moment, the next breath, the next piece of the story still waiting to be lived.